Something is watching us. Not a god, not a creature, something bigger. We stand on a speck of dust, spinning in the dark, asking a question so ancient even the stars seem to whisper it. What is the purpose of the universe? Every atom in your body was forged in a star's death cry. Hydrogen crushed into helium, carbon born in stellar hearts, iron seeded in supernovae. You are not just in the universe, you are the universe questioning itself. When we ask about the purpose of the universe, we delve into a profound and complex question that has intrigued philosophers, scientists, and thinkers for millennia. This inquiry touches on the fundamental nature of existence and our place within the cosmic tapestry. In scientific terms, the universe does not have an inherent purpose or goal. It simply exists and operates according to the laws of physics. The formation of galaxies, stars, and planets is a result of natural processes driven by gravity, nuclear forces, and other fundamental interactions. From this perspective, the universe unfolds without a predetermined plan or intention. However, humans often seek meaning and purpose in their lives and surroundings. This tendency leads us to project the concept of purpose onto the universe itself. We wonder if there is a grand design or a higher reason for the existence of everything we observe. This search for meaning is deeply rooted in human consciousness and has given rise to various philosophical and religious interpretations throughout history. It is important to note that the question of purpose in the universe is ultimately a matter of personal belief and interpretation. While science can explain how the universe works and continues to uncover its mysteries, the concept of purpose remains in the realm of philosophy and individual perspective. The pursuit of this question reflects our innate curiosity and desire to understand our place in the vast cosmic expanse. Purpose in human creations often stems from intentional design, reflecting our goals and desires. We build tools to solve problems, create art to express emotions, and develop technologies to improve our lives. This purpose is clear, defined, and rooted in conscious decision-making. The cosmos, however, presents a different perspective on purpose. The universe operates based on fundamental laws of physics without apparent intent or design. Galaxies form, stars are born and die, and planets orbit not because of a predetermined plan, but as a result of natural processes playing out over billions of years. This lack of inherent purpose in the cosmos does not diminish its wonder or significance. Instead, it highlights the remarkable complexity that can arise from simple rules. The diversity of celestial objects and phenomena we observe is a testament to the power of these fundamental laws operating across vast scales of time and space. Ultimately, the purpose we find in the cosmos is often one we impose ourselves through our quest for knowledge and understanding. Our drive to explore and explain the universe becomes a purpose in itself, transforming the seemingly purposeless expanse of space into a grand cosmic laboratory for human discovery and wonder. The question of whether the universe has a purpose delves into deep philosophical territory. From a scientific standpoint, the universe operates according to physical laws and principles that we can observe and measure. These laws govern the behavior of matter and energy, shaping the cosmos as we know it. However, these laws do not inherently imply purpose or intent. Many scientists argue that the universe simply exists and evolves according to these natural laws without any overarching goal or design. In this view, the concept of purpose is a human construct, not applicable to the universe as a whole. The universe unfolds through a series of cause and effect relationships, driven by fundamental forces and the initial conditions present at its formation. On the other hand, some philosophers and theologians propose that the universe might have a purpose beyond our current understanding. They suggest that the apparent fine-tuning of physical constants and the emergence of complex structures, including life, could indicate some form of cosmic intent. However, these ideas remain speculative and fall outside the realm of scientific inquiry. Ultimately, the question of universal purpose remains open to interpretation. While science can describe how the universe functions, it cannot definitively answer whether it has an inherent purpose. This leaves room for ongoing debate and exploration at the intersection of science, philosophy, and human understanding. Throughout human history, our understanding of the universe's purpose has undergone significant transformations. Ancient civilizations often viewed the cosmos as a realm of gods and divine beings, attributing celestial events to supernatural forces. These early beliefs shaped creation myths and religious practices, with the universe seen as a stage for divine drama. As scientific inquiry advanced, particularly during the Renaissance and Enlightenment periods, our perspective began to shift. Astronomers like Copernicus and Galileo challenged the Earth-centric model, revealing a vast cosmos beyond our planet. This revelation sparked a fundamental change in how we perceived our place in the universe, leading to questions about its origin and purpose. The 20th century brought revolutionary discoveries in physics and cosmology. Einstein's theory of relativity and the development of quantum mechanics reshaped our understanding of space, time, and the fundamental nature of reality. The Big Bang theory emerged, suggesting the universe had a beginning and has been expanding ever since. This scientific model raised new questions about the purpose and ultimate fate of the cosmos. In recent decades, our view has become increasingly complex. While science has uncovered remarkable insights into the universe's structure and evolution, the question of purpose remains elusive. Some scientists argue that the universe simply exists without inherent meaning, while others explore concepts like the anthropic principle, which considers how the universe's properties allow for the existence of life. This ongoing exploration continues to challenge our understanding and push the boundaries of human knowledge. The concept of cosmic purpose has been a subject of debate among scientists and philosophers for centuries. Many scientists approach this question from a purely empirical standpoint, relying on observable evidence and testable hypotheses. From this perspective, the universe appears to operate according to natural laws without any discernible overarching purpose or goal. Some cosmologists argue that the universe simply exists and evolves based on fundamental physical principles, without any inherent meaning or direction. They point to the vast expanses of seemingly empty space and the violent, chaotic nature of cosmic events as evidence against a purposeful design. However, other scientists note the apparent fine-tuning of universal constants and the emergence of complex structures, including life, as potential indicators of some form of cosmic purpose. This view, often associated with the anthropic principle, suggests that the universe may have characteristics specifically conducive to the development of conscious observers. A third perspective attempts to reconcile these viewpoints by proposing that purpose might emerge as a property of complex systems within the universe rather than being inherent to the cosmos itself. This idea suggests that while the universe may not have been created with a specific purpose, the evolution of conscious beings could imbue it with meaning and direction. Throughout history, diverse cultures have grappled with the concept of universal purpose, offering a rich tapestry of interpretations that reflect their unique worldviews and cosmologies. Ancient Egyptian civilization, for instance, saw the universe as a carefully balanced order maintained by the gods, with humans playing a crucial role in upholding cosmic harmony through rituals and proper conduct. In contrast, many Eastern philosophies, such as Buddhism and Taoism, view the universe as an interconnected whole without a specific overarching purpose. These traditions often emphasize the importance of individual enlightenment and harmony with natural cycles rather than a grand cosmic plan. Western monotheistic religions, including Judaism, Christianity, and Islam generally posit a universe created with intention by a supreme being. These faiths often interpret universal purpose as fulfilling divine will or working towards a predetermined end, such as Judgment Day or the perfection of creation. Scientific perspectives, which have gained prominence in recent centuries, tend to approach the question of universal purpose differently. Many scientists argue that the universe operates according to natural laws without an inherent purpose, while others suggest that the increasing complexity and self-awareness observed in cosmic evolution might indicate a form of purpose emerging from the fundamental properties of the universe itself. The search for cosmic purpose appears to be a distinctly human pursuit, rooted in our species' unique capacity for self-awareness and abstract thought. As far as we know, humans are the only beings in the universe who ponder their place in the cosmos and seek meaning beyond mere survival. This quest for understanding our role in the universe stems from our evolved cognitive abilities. Our brains have developed to recognize patterns, make connections, and contemplate abstract concepts like time, infinity, and existence itself. These traits, which have helped us survive and thrive as a species, also drive us to ask profound questions about the nature of reality and our place within it. Interestingly, this search for cosmic purpose often intersects with scientific inquiry. As we explore the universe and uncover its secrets, we inevitably encounter questions about our origins, the nature of consciousness, and the potential for life elsewhere. These scientific pursuits are, in many ways, an extension of our innate desire to understand our place in the cosmic order. While other intelligent species might exist in the universe, we have no evidence that they engage in similar philosophical inquiries. Our search for cosmic purpose remains, as far as we can tell, a uniquely human endeavor that reflects our species' remarkable ability to contemplate the vast and the profound. The immense scale of the universe profoundly shapes our understanding of its purpose and our place within it. As we gaze into the night sky, we see only a tiny fraction of the cosmos, yet even this glimpse reveals a staggering array of stars, galaxies, and celestial phenomena. This vastness challenges our human-centric view of the universe and forces us to reconsider our significance. The sheer number of galaxies, each containing billions of stars, suggests the possibility of countless worlds and potential for life beyond Earth. This realization can be both humbling and awe-inspiring, as it implies that we are part of something far greater than ourselves. The vast distances between celestial objects also highlight the isolation of our planet, emphasizing the preciousness of life as we know it. Moreover, the age of the universe, estimated at nearly 14 billion years, dwarfs human existence. This temporal scale prompts us to contemplate the long-term evolution of the cosmos and our fleeting presence within it. It raises questions about the origin and ultimate fate of the universe, encouraging scientific inquiry and philosophical reflection. The vastness of the universe also reveals the intricate interconnectedness of cosmic processes. From the formation of elements in stellar cores to the gravitational dance of galaxies, we observe a complex system operating on scales far beyond human experience. This perspective can inspire a sense of cosmic unity and purpose, even as it challenges us to find meaning in our seemingly small corner of the universe. The concept of purpose in the universe is a complex and thought-provoking topic that has intrigued scientists and philosophers for centuries. When we consider purpose, we often associate it with conscious intent as seen in human actions and decisions. However, in the broader context of the cosmos, we can indeed separate purpose from conscious intent. In nature, we observe numerous processes and phenomena that appear purposeful without involving conscious decision-making. Evolution by natural selection is a prime example. Over billions of years, life on Earth has developed intricate adaptations and complex ecosystems, all without a conscious guiding hand. The process itself, driven by environmental pressures and genetic variation, leads to outcomes that seem purposeful. Similarly, in physics, we see principles like the conservation of energy or the tendency of systems to move towards equilibrium. These fundamental laws guide the behavior of matter and energy throughout the universe, creating patterns and structures that can appear purposeful. The formation of galaxies, stars, and planets follows these physical laws, resulting in cosmic structures that seem designed but arise from natural processes. This separation of purpose from conscious intent allows us to explore the universe's workings without assuming a cosmic consciousness. It enables scientists to study natural phenomena objectively, seeking explanations based on observable evidence and testable hypotheses. By doing so, we can uncover the underlying principles that shape our universe, revealing a kind of inherent purpose in the very fabric of reality itself. Human consciousness plays a crucial role in our perception and interpretation of the universe, including our tendency to attribute purpose or meaning to cosmic phenomena. Our ability to contemplate our existence and ponder the nature of reality leads us to seek patterns, explanations, and underlying reasons for the universe's structure and behavior. This quest for meaning is a fundamental aspect of human nature, driven by our evolved capacity for abstract thought and pattern recognition. Our consciousness allows us to formulate complex ideas about the cosmos, develop scientific theories, and create philosophical frameworks to understand our place within it. However, it is important to note that the universe itself does not inherently possess purpose or intent. The attribution of purpose is a product of human consciousness rather than an intrinsic property of the cosmos. Scientific inquiry has revealed that many cosmic processes can be explained through natural laws and physical interactions, without the need for overarching purpose or design. Nonetheless, our consciousness-driven search for meaning has been a powerful force in advancing our understanding of the universe. It has motivated scientific exploration, technological development, and philosophical inquiry, ultimately expanding our knowledge of the cosmos and our place within it. The Big Bang Theory, our current best explanation for the origin of the universe, presents a fascinating intersection with the question of cosmic purpose. This scientific model describes the universe expanding from an incredibly hot, dense state about 13.8 billion years ago. However, it does not directly address whether there is an underlying purpose or intent behind this cosmic birth. While the Big Bang provides a framework for understanding the physical evolution of our universe, it remains silent on matters of meaning or purpose. Some view the precise conditions necessary for our universe to form as evidence of design, suggesting a potential cosmic purpose. Others see the Big Bang as a purely natural event, devoid of inherent meaning beyond its physical consequences. The theory does, however, highlight the remarkable chain of events that led to our existence. From the initial expansion to the formation of galaxies, stars, and planets, the Big Bang set the stage for the emergence of life as we know it. This realization prompts us to consider our place in the cosmos and whether our ability to contemplate these questions is itself a form of cosmic purpose. Ultimately, the relationship between the Big Bang and cosmic purpose remains a philosophical question. The theory provides the scientific backdrop against which we can explore these deeper existential inquiries, bridging the realms of physics and philosophy in our quest to understand our cosmic origins and potential purpose. The conditions before the Big Bang remain one of the greatest mysteries in cosmology. Our current understanding of physics breaks down as we approach the moment of the Big Bang, making it challenging to describe what came before. Some theories suggest a state of extreme density and temperature, often called a singularity, where the laws of physics as we know them may not apply. Quantum fluctuations might have played a role in the pre-Big Bang state, potentially giving rise to the expansion that created our universe. Other hypotheses propose the existence of a multiverse, where our Big Bang was just one of many universe-creating events. However, these ideas remain speculative and are difficult to test with current technology. As for the universe's purpose, science does not typically address questions of purpose or meaning, as these fall outside the realm of empirical observation. The conditions before the Big Bang, even if fully understood, would not necessarily inform us about any inherent purpose of the universe. Instead, they might provide insights into the mechanisms that led to its formation and evolution. The quest to understand the pre-Big Bang state continues to drive scientific inquiry, pushing the boundaries of our knowledge about the fundamental nature of reality, space, and time. This ongoing exploration exemplifies humanity's drive to comprehend our cosmic origins and place in the universe. The laws of physics that emerged from the Big Bang provide a framework for understanding the universe's behavior and evolution. These fundamental principles, such as gravity, electromagnetism, and the strong and weak nuclear forces, work together in a remarkably precise and balanced way. This fine-tuning of physical constants and laws has led some scientists and philosophers to ponder whether there might be an underlying purpose or design to the cosmos. One intriguing aspect of these laws is their universality. The same principles that govern the behavior of atoms in laboratories on Earth also apply to distant stars and galaxies billions of light-years away. This consistency across vast scales of space and time suggests a fundamental order to the universe, which some interpret as a sign of purpose or intentionality. Furthermore, the laws of physics appear to be finely tuned to allow for the existence of complex structures, including life as we know it. Small changes in the fundamental constants could result in a universe incapable of supporting stars, planets, or biological organisms. This apparent fine-tuning has sparked debates about the anthropic principle and whether our universe might be one of many in a vast multiverse. However, it's important to note that the appearance of purpose or design in the laws of physics does not necessarily imply a conscious creator or predetermined goal. Many scientists argue that our universe's properties could be the result of random chance or natural processes we don't yet fully understand. The quest to unravel these mysteries continues to drive scientific exploration and philosophical inquiry into the nature of our cosmos. Cosmic inflation is a pivotal concept in our understanding of the universe's early moments and its subsequent evolution. This theory proposes that the universe underwent an incredibly rapid expansion in the tiniest fraction of a second after the Big Bang. During this fleeting instant, the cosmos expanded faster than the speed of light, stretching from a subatomic scale to a size larger than our observable universe today. This extraordinary growth spurt played a crucial role in shaping the universe we see around us. It explains why the cosmos appears remarkably uniform on large scales, solving the horizon problem that had long puzzled cosmologists. Inflation also accounts for the flatness of space and the absence of magnetic monopoles, two observations that were difficult to reconcile with earlier models of the Big Bang. Perhaps most importantly, cosmic inflation provides a mechanism for the formation of large-scale structures in the universe. As the universe expanded, quantum fluctuations were amplified to cosmic scales, creating slight variations in density. These variations became the seeds for the formation of galaxies, galaxy clusters, and the cosmic web of matter we observe today. While inflation does not directly address the question of the universe's purpose, it does offer insights into its fundamental nature. The theory suggests that our observable universe might be just one of many regions within a vastly larger, perhaps infinite, cosmic expanse. This idea opens up intriguing possibilities about the nature of reality and our place within it, prompting us to reconsider our understanding of the cosmos and its potential for harboring other forms of life or even other universes. The concept of multiple universes or a multiverse dramatically expands our perspective on cosmic purpose. This idea suggests that our universe might be just one of countless others, each potentially governed by different physical laws and constants. Such a vast cosmic landscape challenges traditional notions of uniqueness and purpose on a universal scale. In a multiverse scenario, the apparent fine-tuning of our universe for life becomes less miraculous and more a matter of cosmic probability. With an infinite number of universes, the likelihood of one existing with conditions suitable for life increases significantly. This shift in perspective doesn't necessarily negate the idea of purpose, but rather reframes it in a broader context. The multiverse concept also introduces the possibility of alternate versions of ourselves existing in parallel universes, each making different choices and experiencing different outcomes. This notion further complicates our understanding of free will, determinism, and the nature of reality itself. Ultimately, the multiverse theory encourages us to think beyond the confines of our observable universe and consider the possibility of a much grander cosmic tapestry. It invites us to ponder questions of existence, purpose, and meaning on an even more profound scale, pushing the boundaries of our philosophical and scientific understanding. The idea that our universe had a definite beginning is supported by several key pieces of evidence. One of the most compelling is the expansion of the universe, first observed by Edwin Hubble in the 1920s. Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This observation suggests that if we trace the universe's expansion backward in time, everything would converge to a single point. Another crucial piece of evidence is the cosmic microwave background radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1964. This faint glow, present throughout the universe, is the afterglow of the Big Bang itself. Its existence and properties align perfectly with the predictions of the Big Bang theory, providing strong support for a universe with a definite beginning. The abundance of light elements in the universe, particularly hydrogen and helium, also supports the Big Bang theory. The observed ratios of these elements match the predictions of how they would have been created in the extreme conditions of the early universe. This agreement between theory and observation further strengthens the case for a cosmic beginning. Lastly, the distribution of galaxies and large-scale structures in the universe aligns with models of how matter would have clumped together following the Big Bang. Computer simulations based on these models accurately predict the cosmic web of galaxies we observe today, lending additional credence to the idea of a universe with a definite starting point. The universe's initial conditions, set in the earliest moments after the Big Bang, play a crucial role in shaping its long-term evolution and potential purpose. These primordial conditions, including the distribution of matter and energy, the strength of fundamental forces, and the laws of physics, act as a cosmic blueprint that guides the universe's development. One of the most intriguing aspects of these initial conditions is their apparent fine-tuning. The values of certain physical constants and the ratios between fundamental forces seem precisely calibrated to allow for the formation of complex structures like galaxies, stars, and ultimately, life as we know it. This fine-tuning raises profound questions about the universe's purpose and whether it might be inherently biased towards the emergence of complexity and consciousness. The initial conditions also set the stage for the universe's eventual fate. The balance between the expansion rate and the gravitational pull of matter determines whether the universe will continue expanding indefinitely, eventually collapse back on itself, or reach a state of equilibrium. This cosmic destiny, predetermined by the initial conditions, could be seen as part of the universe's overarching purpose, or lack thereof. Furthermore, the initial conditions influence the distribution of matter and energy across the cosmos, leading to the formation of large-scale structures like galaxy clusters and cosmic voids. This cosmic web of matter serves as the scaffolding for the evolution of galaxies and the potential development of life, suggesting that the initial conditions might have set the universe on a path towards increasing complexity and the possibility of conscious observers. While the Big Bang theory remains the most widely accepted explanation for the origin of our universe, several alternative theories have emerged over the years. One such alternative is the steady-state theory, which proposes that the universe has always existed and continues to expand, with new matter constantly being created to maintain a constant density. This theory challenges the idea of a singular cosmic beginning, Another intriguing alternative is the cyclic universe model, which suggests that our universe undergoes endless cycles of expansion and contraction. In this view, the Big Bang represents just one of many cosmic rebirths, with each cycle potentially lasting trillions of years. This concept aligns with some ancient philosophical ideas about the cyclical nature of existence. The holographic universe theory posits that our three-dimensional reality is actually a projection of information stored on a two-dimensional surface, similar to how a hologram works. This mind-bending concept suggests that the universe we perceive might be an illusion, raising profound questions about the nature of reality and our place within it. When it comes to cosmic purpose, these alternative theories offer different perspectives. While they do not inherently ascribe meaning to the universe, they open up new avenues for contemplating our existence. The cyclic universe model, for instance, presents the possibility of multiple cosmic histories and futures, potentially giving rise to different forms of life and consciousness across vast timescales. These theories invite us to consider the universe not as a singular event with a defined purpose, but as an ongoing process of change and evolution, where meaning and purpose might emerge through the complex interactions of matter, energy, and consciousness over time. Quantum fluctuations played a crucial role in shaping the early universe, but their connection to any cosmic purpose remains a subject of philosophical debate. These tiny, random variations in energy and matter arose from the inherent uncertainty of quantum mechanics during the first fractions of a second after the Big Bang. These fluctuations served as the seeds for all cosmic structure we observe today. As the universe expanded and cooled, these minute irregularities grew under the influence of gravity, eventually forming galaxies, stars, and planets. The quantum realm's unpredictability laid the foundation for the rich, diverse cosmos we inhabit. From a scientific perspective, quantum fluctuations do not imply an inherent purpose to the universe. They are a natural consequence of quantum mechanics, occurring without apparent design or intent. However, their existence and effects have led some to ponder deeper questions about the nature of reality and our place within it. The fact that these microscopic fluctuations ultimately led to conditions suitable for life has prompted some to see a purposeful universe. Others view this as an example of the anthropic principle, suggesting we observe these conditions precisely because they allowed us to evolve and observe them. The relationship between quantum fluctuations and cosmic purpose thus remains an open question, bridging the realms of physics and philosophy. The origin of the universe, often traced back to the Big Bang, does indeed offer tantalizing clues about its potential fate and underlying nature. By studying the early moments of cosmic history, scientists have uncovered fundamental principles that shape our understanding of the universe's future. One key insight from the universe's birth is the concept of expansion. Observations show that space itself is stretching, carrying galaxies apart at an accelerating rate. This expansion, which began with the Big Bang, suggests that the universe might continue to grow indefinitely, leading to a possible Big Freeze, where all matter becomes isolated and energy dissipates. However, the ultimate destiny of the universe remains uncertain. The initial conditions set during its formation, including the distribution of matter and energy, play a crucial role in determining its long-term evolution. The discovery of dark energy, a mysterious force driving cosmic acceleration, has further complicated our predictions about the universe's fate. As for purpose, science cannot directly address questions of meaning or intent. Yet, the remarkable fine-tuning observed in physical constants and the emergence of complex structures from simple beginnings continue to fuel scientific inquiry and philosophical discussions about the nature of existence and our place within the cosmos. The four fundamental forces of nature — gravity, electromagnetism, the strong nuclear force, and the weak nuclear force — form the backbone of our universe's structure and behavior. These forces work in concert to shape everything from the tiniest subatomic particles to the largest cosmic structures. Gravity, the weakest yet most far-reaching force, draws matter together on cosmic scales. It is responsible for the formation of galaxies, stars, and planets, creating the environments necessary for complex structures to emerge. Electromagnetism governs the interactions between charged particles, enabling the formation of atoms and molecules, and is crucial for the chemical processes that underpin life as we know it. The strong nuclear force binds quarks together to form protons and neutrons, and holds these particles together within atomic nuclei. This force is essential for the stability of matter and enables the nuclear fusion processes that power stars, producing the heavier elements necessary for planetary formation and life. The weak nuclear force, while less apparent in everyday life, plays a vital role in certain types of radioactive decay and is crucial in stellar nucleosynthesis. These forces, working in delicate balance, have allowed the universe to evolve from a hot, dense state to the complex cosmos we observe today. While science cannot definitively state a purpose for the universe, the interplay of these forces has created conditions conducive to the emergence of structure, complexity, and potentially consciousness. This remarkable outcome might suggest that if the universe has a purpose, it could be to foster the development of systems capable of observing and understanding it. Gravity is the fundamental force that shapes the large-scale structure of the universe. It acts as the cosmic architect, orchestrating the formation and evolution of galaxies, galaxy clusters, and the vast cosmic web that spans the observable universe. On the grandest scales, gravity causes matter to clump together, forming dense regions that eventually become galaxies and galaxy clusters. These clusters are connected by long filaments of gas and dark matter, creating a cosmic web-like structure. The denser regions continue to attract more matter over time, while less dense areas become increasingly empty, forming cosmic voids. Gravity also plays a crucial role in the internal dynamics of galaxies and galaxy clusters. It holds stars together within galaxies and keeps galaxies bound within clusters. The gravitational pull of dark matter, which scientists believe makes up a significant portion of the universe's mass, further enhances these large-scale structures. Interestingly, the effects of gravity on the universe's structure are in constant competition with the expansion of space itself. While gravity pulls matter together, the mysterious force known as dark energy causes the universe to expand at an accelerating rate, influencing the ultimate fate and shape of our cosmic home. The strong nuclear force plays a fundamental role in shaping the universe as we know it. This powerful interaction binds quarks together to form protons and neutrons, which are the building blocks of atomic nuclei. Without the strong force, these particles would fly apart, and atoms as we know them could not exist. In the early moments after the Big Bang, the strong force was crucial in allowing quarks to combine into hadrons, setting the stage for the formation of the first atomic nuclei. As the universe cooled and expanded, this force continued to play a vital role in nuclear fusion within stars, enabling the creation of heavier elements essential for life. The delicate balance of the strong force's strength is particularly intriguing. If it were slightly weaker, protons and neutrons would not bind, and if it were slightly stronger, all protons and neutrons in the universe might fuse into a single giant nucleus. This fine-tuning has led some to speculate about a potential cosmic purpose or design. While the concept of cosmic purpose remains a philosophical question, the strong force undeniably contributes to the rich complexity of matter we observe in the universe. Its role in enabling the existence of stable atoms and the diversity of chemical elements forms the foundation for the emergence of complex structures, including life itself. The weak nuclear force plays a crucial role in shaping the universe as we know it, contributing to its overall purpose of creating complexity and supporting life. This fundamental force of nature is responsible for certain types of radioactive decay, which are essential for the ongoing processes of stellar nucleosynthesis and the production of heavy elements. In stars, the weak force enables the proton-proton chain reaction, a key process in hydrogen fusion that powers our Sun and other main sequence stars. This reaction converts hydrogen into helium, releasing energy that sustains stars for billions of years. Without the weak force, stars would quickly burn out, leaving the universe cold and devoid of the energy needed for life to emerge and thrive. Furthermore, the weak force is involved in supernova explosions, cosmic events that distribute heavy elements throughout the universe. These elements are necessary for the formation of planets, complex molecules, and ultimately, life itself. The weak force's role in these processes highlights its importance in creating a universe capable of supporting diverse structures and organisms. The delicate balance of the weak force with other fundamental forces allows for the existence of stable atoms and the complex chemistry necessary for life. If the strength of the weak force were significantly different, the universe might not have developed the intricate structures we observe today, from galaxies and stars to planets and living beings. Electromagnetism plays a crucial role in shaping the structure of the universe and influences its potential purpose in profound ways. As one of the four fundamental forces of nature, electromagnetism governs the interactions between electrically charged particles, binding electrons to atomic nuclei and holding atoms together to form molecules and larger structures. On cosmic scales, electromagnetic forces are responsible for the formation and behavior of stars. The intense heat and pressure at a star's core are balanced by the electromagnetic repulsion between atoms, preventing the star from collapsing under its own gravity. This delicate equilibrium allows stars to shine for billions of years, providing the energy necessary for life to evolve on planets like Earth. Electromagnetic radiation, including visible light, radio waves, and X-rays, carries information across vast distances in space. This enables us to study distant galaxies, detect exoplanets, and uncover the secrets of the early universe. The cosmic microwave background radiation, a faint electromagnetic echo of the Big Bang, provides crucial evidence for our understanding of the universe's origins and evolution. Furthermore, electromagnetism might play a role in the universe's potential purpose by enabling the complexity necessary for conscious beings to emerge. The intricate dance of electrons in biological systems, governed by electromagnetic forces, allows for the storage and processing of information in living organisms. This suggests that electromagnetism could be a key factor in the development of intelligence and self-awareness in the cosmos. Dark energy is a mysterious force that permeates all of space, pushing the universe apart and causing its expansion to accelerate. This enigmatic energy makes up about 68% of the universe, yet its true nature remains one of the biggest puzzles in modern cosmology. As galaxies and galaxy clusters move farther apart due to this expansion, dark energy appears to grow stronger, exerting an ever-increasing influence on cosmic evolution. This relentless push against gravity suggests that the universe might expand forever, potentially leading to a future where galaxies become so distant that they fade from view. The concept of dark energy challenges our understanding of fundamental physics and raises profound questions about the fate of the universe. Some scientists speculate that dark energy might be a property of space itself, a sort of negative pressure that emerges as space expands. Regarding cosmic purpose, the role of dark energy is a matter of scientific and philosophical debate. While science cannot directly address questions of purpose, the discovery of dark energy has led some to ponder whether the universe's expansion might serve some greater cosmic function we have yet to comprehend. However, many scientists caution against attributing purpose to natural phenomena, emphasizing that our observations of dark energy and cosmic expansion are better understood through the lens of physical laws rather than teleological interpretations. Dark matter plays a crucial role in shaping the universe we see today. This mysterious substance, which does not interact with light or other forms of electromagnetic radiation, exerts a powerful gravitational influence on visible matter. In galaxy formation, dark matter acts as a cosmic scaffold, creating deep gravitational wells that draw in normal matter. As the early universe expanded and cooled, regions with slightly higher concentrations of dark matter began to attract more and more material. These dense areas became the seeds for galaxy formation, pulling in gas and dust, which eventually formed the stars and galaxies we observe. Without dark matter, the universe would likely be a vastly different place, with matter spread out more evenly and fewer large-scale structures. On a larger scale, dark matter forms an intricate cosmic web that spans the universe. This web consists of dense filaments and nodes where galaxies and galaxy clusters tend to accumulate. The spaces between these filaments form vast cosmic voids, creating a sponge-like structure on the grandest scales. This cosmic web guides the flow of matter and energy across the universe, influencing the distribution and movement of galaxies. The gravitational effects of dark matter also help explain the rotation curves of galaxies, which show that outer regions of galaxies rotate faster than expected based on visible matter alone. This additional gravitational pull from dark matter helps hold galaxies together and influences their shapes and sizes. As we continue to study the universe, our understanding of dark matter and its effects on cosmic structure continues to evolve, offering new insights into the fundamental nature of our cosmos. The cosmic web is the largest known structure in the universe, a vast network of interconnected filaments composed of dark matter and galaxies. These filaments stretch across billions of light years, forming a complex web-like pattern that gives the structure its name. Between these filaments lie enormous voids, nearly empty regions of space that further accentuate the web-like appearance. This grand cosmic architecture emerges from the interplay of gravity and the expansion of the universe. Over billions of years, slight variations in the density of matter in the early universe have been amplified, with denser regions attracting more matter and less dense regions becoming increasingly empty. The result is a universe that resembles a sponge-like structure on the grandest scales. The cosmic web structure provides valuable insights into the history and evolution of the universe. Its patterns reflect the distribution of matter in the very early universe, preserving a record of cosmic conditions that existed long before the first stars and galaxies formed. Scientists study these patterns to better understand the nature of dark matter, dark energy, and the fundamental forces that shape our universe. While the cosmic web does not necessarily point to a universal purpose in the traditional sense, its existence and properties do raise intriguing questions about the nature of our universe. The web's remarkable regularity and the way it embodies fundamental physical principles might suggest an underlying order or structure to reality that we are only beginning to comprehend. This vast cosmic structure serves as a reminder of the incredible scale and complexity of the universe, inviting us to ponder our place within this grand cosmic tapestry. Galaxy clusters and superclusters offer a profound glimpse into the grand architecture of our universe. These colossal structures, composed of thousands of galaxies bound together by gravity, serve as cosmic signposts that reveal the underlying framework of the cosmos. At the cluster level, we observe groups of galaxies huddled together, their mutual gravitational attraction creating dense pockets in the fabric of space. These clusters, often spanning millions of light years, contain not only visible matter, but also vast amounts of dark matter and superheated gas. By studying the dynamics within these clusters, scientists gain insights into the distribution of both visible and invisible matter in the universe. Zooming out further, we encounter superclusters, enormous collections of galaxy clusters that stretch across hundreds of millions of light years. These sprawling structures form the largest known gravitationally bound systems in the cosmos. They outline a cosmic web of filaments and voids, revealing the universe's intricate large-scale structure. This web-like pattern is a direct result of the initial quantum fluctuations in the early universe, amplified over billions of years by gravity. By mapping and analyzing these immense structures, cosmologists can test theories about the universe's evolution and composition. The distribution and movement of galaxy clusters and superclusters provide crucial evidence for the existence of dark matter and dark energy, helping scientists refine models of cosmic expansion and the fundamental forces shaping our universe. This knowledge not only deepens our understanding of cosmic organization, but also illuminates the path of the universe's past and future. The distribution of matter in the universe offers intriguing insights into its structure and evolution, but drawing conclusions about a potential purpose requires careful consideration. On the largest scales, matter forms a cosmic web of galaxies, galaxy clusters, and vast filaments separated by enormous voids. This pattern emerged from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. Remarkably, this distribution aligns closely with computer simulations based on our current understanding of physics, suggesting that the universe follows predictable laws. The presence of dark matter, inferred from gravitational effects, plays a crucial role in shaping this cosmic architecture. Its invisible influence guides the formation of galaxies and the large-scale structure we observe. The uniformity of matter distribution on the grandest scales supports the cosmological principle, which states that the universe looks roughly the same in all directions. This homogeneity implies that there is no special location or direction in the cosmos, challenging notions of a central purpose focused on any particular region. While the distribution of matter reveals much about the physics governing our universe, it does not directly indicate an overarching purpose. The patterns we observe are consistent with natural processes acting over immense timescales. As we continue to study the cosmos, we gain a deeper appreciation for its complexity and the fundamental laws that shape it, even if its ultimate purpose remains a philosophical question beyond the realm of scientific inquiry. Stars play a crucial role in shaping the universe and potentially contributing to its purpose. These cosmic furnaces are the primary factories for creating heavier elements, a process known as stellar nucleosynthesis. Through their lives and deaths, stars forge the building blocks necessary for complex structures, planets, and even life itself. During their main sequence phase, stars fuse hydrogen into helium, releasing enormous amounts of energy. As they age, larger stars can produce progressively heavier elements, from carbon and oxygen to iron. When massive stars explode as supernovae, they scatter these elements across space, enriching the interstellar medium. This continuous cycle of stellar birth, life, and death gradually increases the universe's complexity. The heavy elements produced by stars are essential for forming rocky planets, complex molecules, and ultimately, the ingredients for life as we know it. In this way, stars could be seen as crucial components in a cosmic assembly line, potentially working towards increasing universal complexity and the emergence of conscious beings. Furthermore, stars serve as beacons of light in the vast darkness of space, allowing us to study and understand the universe. Their light carries information about the composition, age, and evolution of distant galaxies, helping us piece together the cosmic story. In this sense, stars might contribute to the universe's purpose by enabling the existence of observers who can contemplate and explore its mysteries. Stellar nucleosynthesis stands as a cornerstone in the grand narrative of cosmic evolution. This process, occurring within the fiery hearts of stars, forges the heavier elements essential for the complex structures we see in the universe today. From the carbon in our bodies to the iron in Earth's core, these elements owe their existence to the intense fusion reactions taking place in stellar cores. The significance of stellar nucleosynthesis extends far beyond the stars themselves. It represents a crucial link in the chain of cosmic events that led to our existence. The first generation of stars, composed primarily of hydrogen and helium, manufactured heavier elements and dispersed them into space upon their deaths. These enriched materials then coalesced to form new stars, planets, and eventually, life itself. This process highlights the interconnectedness of all matter in the universe. The atoms in our bodies have quite literally been forged in the crucibles of long-dead stars, connecting us directly to the cosmic narrative. It demonstrates that the universe has evolved from simplicity to complexity, with stars acting as the engines of this transformation. While the concept of cosmic purpose remains a philosophical question, stellar nucleosynthesis provides a scientific framework for understanding our place in the universe. It reveals a cosmos that, through natural processes, has developed the capacity to create the conditions necessary for conscious beings to contemplate their own origins. This realization imbues the study of stars with profound implications for our understanding of cosmic evolution and our place within it. Stars are the cosmic engines that drive the evolution of the universe. Their life cycles, from birth in vast nebulae to their eventual demise, play a crucial role in shaping the cosmos and creating the conditions necessary for life as we know it. When massive clouds of hydrogen and helium collapse under their own gravity, they ignite nuclear fusion, giving birth to new stars. These stellar furnaces forge heavier elements like carbon, oxygen, and iron in their cores through nuclear reactions. As stars age and die, they release these elements into space, enriching the surrounding gas and dust. This process of stellar evolution and element creation is fundamental to the existence of planets, complex molecules, and ultimately, life itself. The atoms in our bodies and the world around us were once forged in the hearts of long-dead stars, connecting us directly to the cosmic narrative. While the universe does not have a predetermined purpose in the traditional sense, the life cycles of stars demonstrate a remarkable interconnectedness. They showcase how the fundamental processes of the cosmos lead to increasing complexity and the potential for life to emerge, suggesting that the universe itself might be a self-organizing system capable of creating the conditions for its own exploration and understanding. Supernovae are cosmic powerhouses that shape the universe in profound ways. These stellar explosions occur when massive stars reach the end of their lives, or when white dwarf stars in binary systems accumulate too much matter. The immense energy released during these events has far-reaching consequences for the cosmos. One of the most significant roles of supernovae is their contribution to the chemical enrichment of the universe. During their explosive deaths, these stars forge and expel heavy elements like iron, gold, and uranium. This process, known as nucleosynthesis, is responsible for creating most of the elements heavier than iron in the universe. These materials then disperse throughout space, eventually forming new stars, planets, and even the building blocks of life. Supernovae also play a crucial role in triggering star formation. The shock waves generated by these explosions compress nearby clouds of gas and dust, causing them to collapse and form new stars. This cosmic cycle of destruction and creation helps drive the ongoing evolution of galaxies and stellar populations throughout the universe. Furthermore, supernovae serve as cosmic distance markers, allowing astronomers to measure vast distances across the universe. Type Ia supernovae, in particular, have a consistent brightness, making them valuable standard candles for cosmic measurements. These observations have led to groundbreaking discoveries, including the accelerating expansion of the universe, which hints at the presence of dark energy and shapes our understanding of cosmic evolution. Galaxies form through a complex process of gravitational attraction and cosmic evolution. In the early universe, slight variations in the density of matter caused regions of greater mass to exert stronger gravitational pull. These areas gradually drew in more material, growing larger and denser over time. As these cosmic nurseries expanded, they began to rotate due to conservation of angular momentum, forming vast disks of gas and dust. Within these rotating disks, pockets of material collapsed under their own gravity, igniting to form the first stars. These stellar nurseries continued to produce new stars, while older generations enriched the surrounding space with heavier elements through supernovae explosions. Over billions of years, this cycle of star formation and destruction shaped the diverse structures we observe in galaxies today. The formation of galaxies reveals the universe's tendency towards increasing complexity and organization. From simple hydrogen and helium, the cosmos has produced intricate systems capable of supporting life. This progression might suggest a cosmic purpose of creating environments where conscious beings can emerge and contemplate their own existence. However, it is important to note that attributing purpose to cosmic processes is a philosophical interpretation rather than a scientific conclusion. The formation of galaxies demonstrates the power of fundamental physical laws to create order and structure on a grand scale, inviting us to ponder our place in this vast and evolving cosmos. Galactic collisions play a crucial role in shaping the universe we observe today. These cosmic encounters, which occur when two or more galaxies come close enough for their gravitational forces to interact, are not as violent as their name might suggest. Instead, they are slow, graceful dances that unfold over millions or even billions of years. These collisions drive the evolution of galaxies in several ways. They trigger bursts of star formation as gas clouds within the colliding galaxies are compressed, creating ideal conditions for new stars to be born. This process can lead to the formation of some of the most massive and brightest stars in the universe. Galactic mergers also contribute to the growth of supermassive black holes at the centers of galaxies. As galaxies collide, large amounts of gas and dust are funneled toward their cores, providing fuel for these cosmic giants to grow even larger. This process can trigger periods of intense activity, turning the merged galaxy into what astronomers call an active galactic nucleus. Furthermore, these cosmic collisions reshape the structure of galaxies. Spiral galaxies, for instance, can be transformed into elliptical galaxies through major mergers. The collision process can also create extended halos of stars and produce long tidal tails, streams of stars and gas that extend far beyond the main body of the merged galaxy. These features serve as cosmic fossils, providing astronomers with valuable clues about a galaxy's collision history and the overall evolution of structure in the universe. Supermassive black holes at the centers of galaxies play a crucial role in shaping cosmic structure on both galactic and intergalactic scales. These colossal objects, with masses ranging from millions to billions of times that of our Sun, exert a profound influence on their surroundings through various mechanisms. One of the most significant ways supermassive black holes affect cosmic structure is through their gravitational pull. Their immense mass creates a deep gravitational well that influences the motion of stars, gas, and dust within the galaxy. This gravitational force helps maintain the structure of the galactic bulge and contributes to the overall stability of the galaxy. Supermassive black holes also drive powerful outflows of energy and matter known as active galactic nuclei. As material falls into the black hole, it forms an accretion disk that heats up to extreme temperatures, releasing enormous amounts of energy. This energy can propel jets of particles and radiation far into intergalactic space, affecting the distribution of matter on vast scales. These outflows can heat surrounding gas, preventing it from cooling and forming new stars, effectively regulating star formation in the galaxy. Furthermore, when galaxies merge, their central black holes also combine, releasing gravitational waves that ripple through space-time. These mergers play a vital role in the growth of cosmic structure as smaller galaxies are absorbed into larger ones, forming the massive galaxies and galaxy clusters we observe today. The interplay between supermassive black holes and galactic evolution thus shapes the large-scale structure of the universe, influencing the cosmic web of galaxies, filaments, and voids that characterizes our cosmos. The Milky Way's structure and composition offer fascinating insights into the workings of the universe, though they do not directly reveal its purpose. Our galaxy, a vast spiral of stars, gas, and dust, spans over 100,000 light-years across. Its composition reflects the cosmic history of star formation and element creation. At the heart of the Milky Way lies a supermassive black hole, surrounded by a dense bulge of older stars. This central region gives way to spiral arms teeming with younger stars, nebulae, and pockets of intense star formation. The varied ages of stars throughout our galaxy showcase the ongoing cycle of stellar birth and death that has occurred over billions of years. The elements found in the Milky Way tell a story of cosmic evolution. While the early universe contained primarily hydrogen and helium, successive generations of stars have forged heavier elements through nuclear fusion and supernova explosions. The presence of these elements in our galaxy demonstrates the intricate processes that have shaped the cosmos and ultimately made life possible. Studying the Milky Way's structure and composition reveals the fundamental forces and processes at work in the universe. It shows us how gravity shapes large-scale structures, how stars form and evolve, and how the elements necessary for life are created and distributed. While these observations do not point to an overarching purpose, they do highlight the incredible complexity and interconnectedness of the cosmos. Intergalactic voids are vast regions of space that contain very few or no galaxies. These enormous cosmic deserts, spanning hundreds of millions of light-years, play a crucial role in shaping our understanding of the universe's structure and evolution. These voids act as negative imprints of the cosmic web, highlighting the areas where matter is not present. By studying these empty regions, astronomers can better comprehend the distribution of matter throughout the universe. This insight helps refine models of cosmic evolution and the formation of large-scale structures. Voids also serve as natural laboratories for testing theories of gravity and dark energy. The behavior of the few galaxies found within these regions can reveal important clues about the nature of these fundamental forces. Additionally, the expansion rate of voids over time provides valuable data on the overall expansion of the universe. Furthermore, the existence of these enormous empty spaces challenges our understanding of galaxy formation and evolution. By examining the properties of the rare galaxies found within voids, scientists can gain insights into how environment affects galactic development, potentially uncovering new aspects of astrophysics and cosmology. Globular clusters are ancient spherical collections of stars that orbit the centers of galaxies. These cosmic relics, some nearly as old as the universe itself, play a crucial role in our understanding of galactic evolution and structure. As remnants of the early universe, globular clusters provide astronomers with valuable insights into the formation and development of galaxies. They serve as cosmic time capsules, preserving information about the chemical composition and age of the universe when they formed. By studying these clusters, scientists can trace the history of star formation and the distribution of elements throughout cosmic time. Globular clusters also influence the dynamics of their host galaxies. As they orbit through the galactic halo, they interact with other stars and structures, potentially altering the galaxy's shape and composition over billions of years. Some theories suggest that globular clusters might even contribute to the growth of supermassive black holes at the centers of galaxies by funneling stars towards the galactic core. While it is challenging to ascribe a universal purpose to cosmic phenomena, globular clusters undoubtedly play a significant role in shaping our understanding of the universe. They serve as natural laboratories for studying stellar evolution, dark matter distribution, and the fundamental laws of physics under extreme conditions. As we continue to unravel their mysteries, globular clusters may hold the key to answering some of the most profound questions about our cosmic origins and the ultimate fate of the universe. Planet formation is a crucial process in the cosmic tapestry, offering insights into the potential purpose of the universe. As gas and dust coalesce around young stars, they gradually build up into rocky worlds and gas giants, creating the diverse array of planets we observe today. This process, occurring throughout galaxies, suggests that the universe might have an inherent tendency to create complex structures from simpler components. The formation of planets provides environments where the chemistry of life can potentially unfold. Earth, our home planet, demonstrates how these cosmic nurseries can give rise to conditions suitable for the emergence and evolution of living organisms. The discovery of thousands of exoplanets orbiting distant stars indicates that planet formation is a common occurrence, hinting at the possibility of life beyond our solar system. Moreover, planet formation contributes to the increasing complexity of the universe over time. From the relatively simple conditions following the Big Bang, the cosmos has evolved to include intricate systems like planetary bodies, which in turn can support even more complex phenomena such as weather patterns, geological processes, and potentially biological evolution. While we cannot definitively state the purpose of the universe, the ubiquity of planet formation suggests that the creation of stable, potentially life-supporting environments might be an integral part of cosmic evolution. This perspective invites us to consider our place in the universe not as mere observers, but as participants in an ongoing process of cosmic creativity and complexity. For a planet to potentially harbor life as we know it, several key conditions must be met. First and foremost, the planet needs to be in the habitable zone of its star, where temperatures allow for liquid water to exist on the surface. This Goldilocks region is not too hot and not too cold, providing a crucial foundation for life to develop. The presence of a stable atmosphere is another vital factor. An atmosphere helps regulate temperature, protects the surface from harmful radiation, and can provide necessary gases for life processes. The planet should also have a magnetic field, which shields it from cosmic radiation and helps retain its atmosphere. The planet's composition plays a significant role in its potential to support life. It should have a rocky core and be large enough to maintain its own heat and geological activity. This internal heat drives processes like plate tectonics, which can regulate the planet's carbon cycle and maintain long-term climate stability. Lastly, the presence of organic compounds and a diverse range of elements is crucial. These building blocks of life, including carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, provide the necessary ingredients for complex molecules to form and potentially give rise to living organisms. While these conditions are based on our understanding of life on Earth, they serve as a starting point in the search for life beyond our planet. The concept of habitable zones and the idea of cosmic purpose intersect in fascinating ways, sparking deep questions about life in the universe. Habitable zones, often called Goldilocks zones, are regions around stars where conditions might be just right for life as we know it to exist. These areas are neither too hot nor too cold, potentially allowing for liquid water on a planet's surface, a key ingredient for life as we understand it. When we consider habitable zones in the context of cosmic purpose, we delve into profound philosophical territory. The very existence of these zones suggests that the universe might possess conditions favorable for life, leading some to ponder whether this is mere coincidence or indicative of some greater design. Scientists have discovered numerous planets within the habitable zones of their stars, fueling speculation about the potential for extraterrestrial life. However, the presence of habitable zones does not necessarily imply a cosmic purpose. Many scientists argue that in a vast universe with countless stars and planets, the emergence of conditions suitable for life is statistically likely rather than the result of intentional design. This perspective aligns with the principle of mediocrity, which suggests that Earth and its life forms are not inherently special or unique in the cosmos. Ultimately, the relationship between habitable zones and cosmic purpose remains a subject of ongoing debate and exploration. While habitable zones provide tantalizing possibilities for life beyond Earth, whether they point to a greater purpose in the universe or are simply a product of cosmic chance, continues to captivate scientists, philosophers, and the public alike. Gas giants are massive planets primarily composed of hydrogen and helium, and they play a crucial role in shaping solar systems. These behemoths exert significant gravitational influence on their cosmic neighborhoods, affecting the orbits and development of other celestial bodies. One of the most important functions of gas giants is their ability to act as cosmic shields for smaller, rocky planets like Earth. Their immense gravitational pull can attract and capture incoming comets, asteroids, and other potentially hazardous objects, effectively reducing the number of impacts on inner planets. This protective role may have been vital in allowing life to develop and thrive on Earth by reducing catastrophic collisions during the early stages of our solar system. Gas giants also play a key role in the formation and evolution of solar systems. During the early stages of planetary formation, these massive planets can migrate inward or outward, disrupting the orbits of smaller bodies and influencing the distribution of material throughout the system. This process can lead to the ejection of some objects from the solar system while causing others to settle into stable orbits. Furthermore, the presence of gas giants can affect the composition and characteristics of other planets in the system. Their strong gravitational fields can influence the movement of gases and dust in the protoplanetary disk, potentially altering the materials available for planet formation in different regions of the solar system. This dynamic interplay between gas giants and their surroundings continues to shape our understanding of how planetary systems form and evolve over time. Asteroid and comet impacts have played a crucial role in shaping the evolution of planets and moons throughout our solar system. These cosmic collisions have left their mark on virtually every celestial body, from the heavily cratered surface of Mercury to the scarred face of our own moon. On Earth, impact events have significantly influenced the course of life. The most famous example is the Chicxulub impact that occurred 66 million years ago, which led to the extinction of the dinosaurs and paved the way for the rise of mammals. However, impacts have not only been harbingers of destruction. Some scientists theorize that comets and asteroids may have delivered water and organic compounds to early Earth, potentially providing the building blocks for life. Beyond our planet, impact events continue to shape the surfaces and compositions of other worlds. On Mars, enormous impact basins like Hellas Planitia have altered the planet's geology and atmosphere. The constant bombardment of Jupiter's moon Europa fractures its icy surface, possibly allowing materials from its subsurface ocean to reach the surface and creating conditions that could be favorable for life. These cosmic collisions also provide valuable information to scientists. By studying impact craters and their surrounding areas, researchers can gain insights into the composition and history of planetary bodies. This knowledge not only helps us understand how planets form and evolve, but also informs our search for potentially habitable worlds beyond Earth. Exoplanets offer a wealth of information about the potential for life beyond Earth. These distant worlds, orbiting stars other than our Sun, provide crucial insights into the diversity of planetary systems and the conditions that might support life as we know it. The sheer number of exoplanets discovered so far suggests that planets are common in the universe. This abundance increases the likelihood of finding worlds with conditions similar to Earth. Scientists have identified many exoplanets within the habitable zones of their stars, where temperatures could allow liquid water to exist on the surface, a key ingredient for life as we understand it. Studying exoplanet atmospheres reveals their chemical compositions, helping scientists determine if they possess the necessary elements for life. Some exoplanets show signs of water vapor, methane, and other organic compounds, hinting at the possibility of biological processes. The variety of exoplanets discovered, from gas giants to rocky worlds, demonstrates the diverse environments that could potentially harbor life. However, exoplanets also highlight the unique nature of Earth. While many planets exist in habitable zones, factors such as a stable atmosphere, magnetic field, and geological activity all contribute to Earth's life-supporting qualities. By comparing exoplanets to our own world, scientists can better understand what makes a planet truly habitable and refine their search for extraterrestrial life. Planetary migration plays a crucial role in shaping solar systems and influencing the conditions necessary for life to emerge. As planets move from their original orbits, they can dramatically alter the environment of other worlds, creating both opportunities and challenges for the development of life. When large gas giants migrate inward, they often push smaller, rocky planets closer to their star, or even eject them from the system entirely. This process can move potentially habitable worlds into the Goldilocks zone, where liquid water can exist on their surfaces, a key ingredient for life as we know it. Conversely, it can also push planets out of this habitable zone, rendering them too cold for life to thrive. Migrating planets can also affect the delivery of water and organic compounds to inner planets. As they move, they can scatter comets and asteroids, either directing them towards the inner solar system or deflecting them away. This process can provide essential building blocks for life to worlds that might otherwise lack them, or it can bombard planets with impacts that could sterilize their surfaces. The gravitational influence of migrating planets can also induce tidal heating in smaller worlds, potentially creating subsurface oceans on moons or other bodies that would otherwise be frozen. These hidden oceans, like those suspected to exist on some of Jupiter's and Saturn's moons, could provide environments where life might develop, even in the cold outer reaches of a solar system. Moons can play a crucial role in creating environments that might support life. These natural satellites influence their parent planets in various ways, potentially making them more hospitable for living organisms. One significant contribution of moons is their ability to stabilize a planet's axis tilt. This stability can lead to more consistent seasons and climate patterns, which are essential for the development and sustenance of life. Earth's moon, for instance, helps maintain our planet's axial tilt, contributing to the relatively stable climate we experience. Tidal forces generated by moons can also be beneficial. These forces can heat a planet's or moon's interior through tidal friction, potentially maintaining liquid water beneath icy surfaces. This phenomenon is observed on Jupiter's moon Europa, where a subsurface ocean exists despite the moon's frigid exterior. Such environments could potentially harbor microbial life. Furthermore, moons can provide protection from cosmic impacts by attracting and absorbing some of the space debris that might otherwise collide with their parent planets. This shielding effect could give life a better chance to evolve and thrive without frequent catastrophic interruptions. Planetary magnetic fields play a crucial role in shielding potential life from harmful cosmic radiation. These fields are generated deep within a planet's core through a process called the dynamo effect. As a planet rotates, the motion of electrically conductive fluids in its core creates powerful electric currents, which in turn produce a magnetic field that extends far into space. This magnetic field acts as a protective bubble around the planet, deflecting high-energy particles from solar winds and cosmic rays. Without this shield, these particles would bombard the planet's surface and atmosphere, potentially damaging or destroying fragile organic molecules and living organisms. The magnetic field also helps prevent atmospheric loss, which is essential for maintaining conditions suitable for life as we know it. Earth's magnetic field is a prime example of this protective mechanism. It has shielded our planet for billions of years, allowing life to evolve and thrive. In contrast, Mars lost its global magnetic field early in its history, leading to the gradual erosion of its atmosphere by solar winds. This loss of atmosphere significantly reduced the planet's ability to support liquid water on its surface, making it far less hospitable to life. The strength and stability of a planet's magnetic field can therefore be a crucial factor in determining its potential habitability. When searching for potentially life-bearing worlds beyond our solar system, scientists consider the presence of a strong magnetic field as one of the key indicators of a planet's ability to sustain life over long periods. Extremophiles on Earth provide valuable insights into the potential for life in the seemingly inhospitable environments of other planets and moons. These remarkable organisms thrive in conditions once thought to be incompatible with life, such as extreme heat, cold, pressure, acidity, or salinity. By studying how extremophiles adapt and survive, scientists can expand their understanding of the limits of life and the diverse forms it might take beyond our planet. The discovery of organisms living in deep-sea hydrothermal vents, for instance, has revolutionized our concept of where life can exist. These creatures survive in complete darkness, under immense pressure, and in water near boiling temperatures. This finding suggests that similar environments on other worlds, such as the subsurface oceans of icy moons like Europa or Enceladus, could potentially harbor life. Microbes found in the driest deserts and the coldest regions of Earth demonstrate that life can persist in environments with limited water and extreme temperatures. This resilience raises the possibility of microbial life existing in the harsh conditions of Mars or other seemingly barren worlds. The ability of certain extremophiles to withstand high levels of radiation also hints at the potential for life to survive on planets with thin atmospheres or those exposed to intense cosmic radiation. Furthermore, the study of extremophiles has expanded our understanding of the chemical processes that can support life. Some organisms use alternative energy sources, such as hydrogen or methane, instead of sunlight. This knowledge broadens the range of environments where we might search for life, including subsurface habitats or atmospheres rich in these alternative energy sources. By learning from Earth extremophiles, scientists can refine their search for extraterrestrial life and develop more effective tools for detecting potential biosignatures on other worlds. The emergence of life in the universe is a profound and complex phenomenon that continues to captivate scientists and philosophers alike. When we consider life in relation to the potential purpose of the universe, we enter a realm where scientific inquiry meets philosophical contemplation. From a scientific perspective, life appears to be an emergent property of complex chemical systems under specific conditions. The universe, with its vast array of galaxies, stars, and planets, provides numerous opportunities for these conditions to arise. As we observe the intricate processes that led to life on Earth, we can speculate about similar processes occurring elsewhere in the cosmos. Some scientists propose that the universe might possess properties that inherently favor the development of life. This idea, known as the anthropic principle, suggests that the fundamental constants and laws of physics we observe are precisely tuned to allow for the existence of life. However, this concept remains highly debated and does not necessarily imply an intentional purpose. Ultimately, the question of whether the emergence of life relates to a cosmic purpose ventures beyond the realm of empirical science. While we can study the mechanisms and conditions that give rise to life, attributing purpose to these processes remains a matter of personal belief and philosophical interpretation. The wonder of life's existence continues to drive our exploration of the cosmos, inspiring us to search for other habitable worlds and ponder our place in the grand tapestry of the universe. Life as we know it requires several crucial elements and conditions to emerge. Water is often considered the most essential ingredient, serving as a universal solvent that facilitates chemical reactions and provides a medium for organic molecules to interact. Carbon forms the backbone of all known life, thanks to its unique ability to form complex, stable molecules with various other elements. Energy is another vital component, typically derived from sunlight or chemical reactions. This energy drives the metabolic processes that sustain living organisms. Nitrogen, phosphorus, and sulfur also play critical roles in forming amino acids, nucleic acids, and other biological molecules. The right temperature range is crucial for life to develop and thrive. Extremely high or low temperatures can denature proteins and disrupt cellular processes. A stable environment that protects against harmful radiation and allows for the accumulation of complex organic molecules is also necessary. Time is an often overlooked but critical factor. The formation of complex organic molecules and the evolution of self-replicating systems require immense spans of time, potentially millions or even billions of years. These conditions, combined with the laws of chemistry and physics, set the stage for the remarkable emergence of life as we understand it. Abiogenesis, the idea that life arose from non-living matter, is a crucial concept in our quest to understand life's origins. This process describes how simple organic compounds could have formed and eventually developed into the complex, self-replicating organisms we see today. The study of abiogenesis has led scientists to explore various scenarios for the emergence of life on Earth. One prominent theory suggests that life might have begun in the primordial soup of ancient oceans, where energy from lightning, ultraviolet radiation, or hydrothermal vents could have sparked chemical reactions. These reactions potentially created amino acids, the building blocks of proteins, and other organic molecules essential for life. Research into abiogenesis has also prompted investigations into alternative environments where life might have originated, such as clay surfaces or ice formations. These studies have expanded our understanding of the conditions necessary for life to emerge and thrive, informing our search for life elsewhere in the universe. By examining the chemical and physical processes involved in abiogenesis, scientists gain insights into the fundamental nature of life itself. This knowledge not only sheds light on our own origins, but also helps us recognize the potential for life in diverse environments beyond Earth. Chemical evolution forms a crucial bridge between the non-living world of simple molecules and the complex, self-replicating systems we recognize as life. This process involves the gradual increase in complexity of chemical compounds in the primordial environment of early Earth. The story begins with the formation of simple organic molecules from inorganic precursors. These basic building blocks, such as amino acids and nucleotides, emerge through reactions driven by energy sources like ultraviolet radiation, lightning, and geothermal heat. Over time, these molecules combine to form more complex structures, including polymers like proteins and nucleic acids. A key step in chemical evolution was the development of molecular self-organization. This allowed for the formation of primitive cell-like structures such as protocells or microspheres, which could concentrate organic molecules and provide a protected environment for further chemical reactions. These early compartments may have facilitated the emergence of rudimentary metabolic processes and information storage systems. The transition from complex organic molecules to the first true living organisms likely involved the emergence of self-replicating molecules, possibly RNA or similar compounds. These molecules could both store information and catalyze chemical reactions, setting the stage for the development of more sophisticated biological systems. Chemical evolution thus laid the groundwork for the origin of life, creating the conditions necessary for the emergence of the first primitive organisms on Earth. Biological evolution is the driving force behind the incredible diversity and complexity of life we see on Earth today. This process, occurring over billions of years, has shaped every living organism, from the tiniest bacteria to the largest whales. At its core, evolution works through natural selection. Organisms with traits that are better suited to their environment are more likely to survive and reproduce, passing these beneficial traits to their offspring. Over time, this leads to the accumulation of advantageous characteristics within a population. Genetic mutations and recombination provide the raw material for evolution. These changes in DNA can create new traits or modify existing ones. While many mutations are neutral or harmful, some prove beneficial, allowing organisms to adapt to new challenges or exploit new opportunities in their environment. As populations become isolated or face different environmental pressures, they can evolve in distinct ways. This process, known as speciation, leads to the formation of new species and contributes significantly to the diversification of life. The complexity of organisms also increases as evolution favors the development of specialized organs and intricate biological systems that enhance survival and reproduction in specific ecological niches. The RNA world hypothesis offers a compelling explanation for how life might have begun on Earth. This idea suggests that before DNA and proteins emerged, RNA molecules played a central role in both storing genetic information and catalyzing chemical reactions. RNA's dual capability as both a genetic material and a catalyst makes it a prime candidate for the first self-replicating molecules that could have led to the development of life as we know it. Scientists have found evidence supporting this hypothesis in several ways. Ribozymes, which are RNA molecules capable of catalyzing chemical reactions, have been discovered in nature and created in laboratories. These findings demonstrate that RNA can indeed perform some of the functions typically associated with proteins. Additionally, researchers have identified RNA sequences that can catalyze their own replication, a crucial step in the emergence of self-sustaining life. The RNA world hypothesis also helps explain the transition to the current DNA-RNA protein system of life. It suggests that DNA eventually took over the role of information storage due to its greater stability, while proteins became the primary catalysts because of their versatility and efficiency. RNA, in this scenario, would have gradually shifted to its current role as an intermediary between DNA and proteins. Understanding the potential role of RNA in life's origins has significant implications for our search for life elsewhere in the universe. It suggests that we should look for signs of RNA-based life or its precursors when exploring other planets and moons, broadening our perspective on what forms extraterrestrial life might take. Horizontal gene transfer is a remarkable process that allows organisms to acquire genetic material from sources other than their parents. This mechanism plays a crucial role in the evolution and spread of life, particularly among microorganisms like bacteria and archaea. Unlike vertical gene transfer, where genetic information is passed from parent to offspring, horizontal gene transfer enables the exchange of genes between unrelated species. This process can occur through various methods, including transformation, where cells take up DNA from their environment, conjugation, where genetic material is transferred directly between cells, and transduction, where viruses act as carriers of genetic information. The impact of horizontal gene transfer on evolution is profound. It accelerates the spread of beneficial traits such as antibiotic resistance in bacteria, allowing organisms to adapt rapidly to new environments. This process can lead to the emergence of new species and contribute to the incredible diversity of life we observe on Earth. Horizontal gene transfer also challenges our traditional understanding of the tree of life. Instead of a simple branching structure, the relationships between species can be viewed as a complex web, with genes flowing not only vertically but also horizontally across different branches. This interconnected network of genetic exchange highlights the dynamic and interconnected nature of life on our planet. Extremophiles have revolutionized our understanding of life's resilience and adaptability. These remarkable organisms thrive in conditions once thought inhospitable to life, such as extreme heat, cold, pressure, and acidity. By studying extremophiles, scientists have expanded the boundaries of what we consider habitable environments, both on Earth and potentially beyond. The discovery of extremophiles has profound implications for the search for extraterrestrial life. If life can exist in Earth's most extreme environments, it might also survive on other celestial bodies with seemingly harsh conditions. This possibility has led scientists to reconsider the criteria for habitable zones around stars and has broadened the scope of potentially life-bearing worlds in our universe. Extremophiles also offer insights into the origins of life on Earth and its potential cosmic purpose. Some scientists speculate that life might have originated in extreme environments, such as deep-sea hydrothermal vents, where certain extremophiles still thrive today. This hypothesis suggests that life might be a natural consequence of specific chemical and physical conditions rather than a chance occurrence. Furthermore, the study of extremophiles has revealed the incredible adaptability of life at the molecular level. These organisms possess unique biochemical mechanisms that allow them to withstand extreme conditions. Such adaptations demonstrate the power of evolution and the potential for life to arise and persist in a wide range of environments across the cosmos, hinting at a possible universal tendency for life to emerge and evolve wherever conditions permit. Panspermia is a fascinating hypothesis that proposes life might have spread throughout the universe by hitching rides on asteroids, comets, or other celestial objects. This concept suggests that the seeds of life, such as microorganisms or organic compounds, could potentially travel vast distances through space, surviving the harsh conditions and eventually landing on habitable planets or moons. The idea of panspermia challenges our understanding of how life began on Earth and raises intriguing possibilities about the interconnectedness of life across cosmic distances. If true, it would mean that life on our planet might share a common origin with potential life forms elsewhere in the galaxy or even beyond. Proponents of panspermia point to the resilience of certain microorganisms on Earth, which can survive extreme conditions similar to those found in space. Some bacteria and tardigrades, for example, can withstand intense radiation, extreme temperatures, and the vacuum of space, lending credibility to the idea that simple life forms could endure interplanetary or even interstellar journeys. While panspermia remains a hypothesis, it opens up exciting avenues for exploration in astrobiology and the search for extraterrestrial life. If life can indeed spread between celestial bodies, it increases the possibility that we might find familiar biological signatures on other worlds within our solar system or even on exoplanets orbiting distant stars. The study of Earth's early life forms provides crucial insights into the potential for life beyond our planet. By examining the most ancient organisms on Earth, scientists can understand the conditions necessary for life to emerge and thrive in extreme environments. Microorganisms that lived billions of years ago, when Earth was a very different place, offer clues about the types of life we might find on other worlds. These early life forms, known as extremophiles, survived in conditions once thought inhospitable to life, such as highly acidic waters, extreme temperatures, or environments devoid of oxygen. The discovery of organisms living near deep-sea hydrothermal vents has expanded our understanding of where life can exist. These ecosystems, thriving in complete darkness and under immense pressure, suggest that similar habitats on other planets or moons could potentially harbor life. For instance, the subsurface oceans of icy moons like Europa or Enceladus might host microbial communities analogous to those found in Earth's deep oceans. Furthermore, studying the chemical signatures left behind by ancient microbes helps scientists identify potential biosignatures on other planets. This knowledge guides the search for extraterrestrial life by informing what to look for in the atmospheres and surfaces of distant worlds, bringing us closer to answering the question of whether we are alone in the universe. The emergence of consciousness in the universe is a profound and complex topic that intersects with our understanding of cosmic purpose. As self-aware beings, humans have long pondered whether our existence and ability to perceive and reflect on the universe might be connected to some greater cosmic design. From a scientific perspective, consciousness appears to be an emergent property of highly complex information processing systems, such as the human brain. This suggests that as the universe evolved and became more complex over billions of years, it eventually gave rise to conditions that allowed for the development of conscious beings. Some scientists and philosophers argue that this could be seen as a natural progression of cosmic evolution, where the universe develops the means to observe and understand itself. However, the idea of a purposeful universe remains a subject of debate. While some view consciousness as evidence of cosmic intention, others see it as a fascinating but ultimately random outcome of natural processes. The anthropic principle, which notes that the universe must have properties that allow for the emergence of observers, further complicates this discussion by suggesting that our very ability to contemplate these questions is tied to the specific conditions of our universe. Ultimately, the relationship between consciousness and cosmic purpose remains an open question, bridging scientific inquiry, philosophy, and our deepest wonderings about our place in the universe. As we continue to explore and understand both the cosmos and the nature of consciousness, we may gain new insights into this profound and captivating mystery. The search for intelligent life beyond Earth intertwines with our quest to understand cosmic purpose. As we explore the universe, we ponder whether other civilizations might have insights or technologies that could unlock deeper mysteries about existence itself. Advanced alien societies, if they exist, might have probed further into the fabric of reality, potentially uncovering fundamental truths about the cosmos that we have yet to grasp. Their scientific and philosophical advancements could provide new perspectives on the nature of consciousness, the origin of the universe, or even the possibility of multiple universes. Intelligent life forms across the cosmos might also be engaged in large-scale projects that shape the evolution of galaxies or harness the energy of stars. Such endeavors could reveal purposes or patterns in cosmic evolution that are not yet apparent to us. The discovery of a galactic community of intelligent species could dramatically reshape our understanding of our place in the universe and any overarching cosmic narrative. However, it is equally possible that we humans are among the first intelligent species to contemplate these questions. In this case, our role might be to pioneer the exploration of cosmic purpose, setting the stage for future civilizations to build upon our discoveries and insights. The development of technology by intelligent species across the universe could be seen as a natural extension of cosmic evolution. As planets form and life emerges, the rise of intelligence and subsequent technological advancement might be viewed as the next step in the universe's journey towards increasing complexity and organization. Intelligent species, through their technological innovations, gain the ability to manipulate their environment on ever larger scales. This progression allows them to harness more energy, explore further into space, and potentially even influence the development of other worlds. In this way, technologically advanced civilizations might be seen as the universe's way of understanding and shaping itself. However, it's important to note that the concept of universal purpose is highly speculative. We cannot say with certainty whether the cosmos has any inherent goal or direction. The development of technology could simply be a consequence of the laws of physics and chemistry playing out over billions of years, rather than serving a predetermined purpose. Nonetheless, the fact that technology allows intelligent species to observe, study, and potentially influence the universe on cosmic scales is remarkable. It raises intriguing questions about the role of consciousness and intelligence in the grand tapestry of existence, and whether our technological endeavors might be part of a larger cosmic narrative yet to be fully understood. Self-awareness stands as a remarkable phenomenon in the universe, representing a way for the cosmos to perceive and understand itself. Through the emergence of conscious beings like humans, the universe has developed the capacity to contemplate its own existence and unravel its mysteries. This self-reflective ability allows us to explore the fundamental questions of our origins, the nature of reality, and our place within the cosmic tapestry. The significance of self-awareness extends beyond mere introspection. It enables us to formulate complex theories about the universe, develop sophisticated technologies to probe its depths, and even ponder the possibility of other forms of consciousness beyond Earth. Our ability to be aware of our own existence and to question our purpose within the cosmos drives scientific inquiry and philosophical contemplation. From a cosmic perspective, self-awareness might be seen as a natural progression in the evolution of complexity in the universe. Starting from simple subatomic particles, progressing through atoms, molecules, and eventually to living organisms, the development of self-aware entities represents a new level of cosmic organization. This progression raises intriguing questions about whether consciousness is a fundamental aspect of the universe or an emergent property of complex systems. The existence of self-aware beings also introduces the concept of cosmic responsibility. As we become increasingly aware of our impact on our planet and potentially beyond, we are faced with ethical considerations about our role in shaping the future of life in the universe. This awareness challenges us to consider not just our individual purpose, but our collective purpose as a species within the grand cosmic narrative. Throughout the cosmos, intelligence manifests in countless forms, each potentially playing a unique role in the grand tapestry of existence. From the microscopic neural networks of Earth's simplest organisms to hypothetical superintelligent civilizations spanning entire galaxies, the universe teems with varying levels of cognition and awareness. These diverse intelligences might collectively contribute to the universe's purpose in ways we can scarcely imagine. Some may act as cosmic gardeners, cultivating life on barren worlds. Others could serve as galactic archivists, preserving the knowledge and history of countless civilizations. Advanced intelligences might even manipulate the fabric of space-time itself, shaping the very structure of the universe. Interstellar cooperation between different forms of intelligence could lead to unprecedented scientific and technological breakthroughs. This collaboration might unlock the secrets of dark matter, harness the power of black holes, or even discover methods to transcend the limitations of our current understanding of physics. Perhaps the ultimate contribution of universal intelligence is to provide the cosmos with a means of self-reflection and understanding. As each form of intelligence observes, analyzes, and interacts with its environment, the universe may be gradually awakening to its own existence, using the collective consciousness of all its inhabitants as a vast cosmic mind. Problem-solving ability plays a crucial role in the evolution of intelligent life. As organisms face challenges in their environments, those with superior problem-solving skills are more likely to survive and pass on their genes. This cognitive capacity allows creatures to adapt to changing conditions, find food, avoid predators, and navigate complex social structures. Throughout evolutionary history, species that developed more advanced problem-solving abilities gained significant advantages. For example, early humans who could create tools, control fire, and develop language were able to thrive in diverse environments. These skills allowed them to hunt more effectively, protect themselves from the elements, and communicate complex ideas. The development of problem-solving skills is closely linked to the growth of brain size and complexity in many species. As brains evolved to process more information and make connections between different concepts, animals became better equipped to tackle increasingly complex challenges. This cognitive arms race has led to the emergence of highly intelligent species like dolphins, elephants, and primates. In the context of potential extraterrestrial life, problem-solving ability might be a universal trait of advanced civilizations. The capacity to overcome obstacles, innovate, and adapt could be essential for any species to develop technology, explore their surroundings, and potentially reach out into the cosmos. The human capacity for abstract thought plays a crucial role in our quest to understand cosmic purpose. This unique cognitive ability allows us to contemplate concepts beyond our immediate physical reality, enabling us to ponder the vast scales of the universe and our place within it. Abstract thinking permits us to grasp complex ideas like infinity, multiple dimensions, and the nature of time itself. These concepts are fundamental to comprehending the cosmos and its potential purpose. By engaging in abstract thought, we can formulate hypotheses about the origin and fate of the universe, considering possibilities that extend far beyond our everyday experiences. Furthermore, our capacity for abstraction enables us to recognize patterns and connections across different scales of existence. This ability helps us draw parallels between microscopic quantum phenomena and the behavior of galaxies, potentially revealing underlying principles that govern the cosmos. Such insights might lead us closer to understanding whether there is an overarching purpose to the universe, or if its existence is the result of random chance. However, it is important to note that while abstract thought allows us to explore cosmic purpose, It also highlights the limitations of human understanding. The sheer scale and complexity of the universe often defy our ability to fully comprehend it, reminding us that our search for cosmic purpose is an ongoing journey of discovery and wonder. Collective intelligence, when considered in the context of the universe, opens up fascinating possibilities for the advancement of knowledge and understanding. As we observe the cosmos, we see examples of collective behavior in various forms, from the synchronized movements of celestial bodies to the complex interactions within galactic structures. On Earth, we witness collective intelligence in action through scientific collaboration and the pooling of human knowledge. This approach has led to groundbreaking discoveries about our universe, from the detection of gravitational waves to the exploration of distant planets. As we extend our gaze beyond our planet, the potential for collective intelligence to unlock cosmic mysteries becomes even more intriguing. Imagine a future where advanced civilizations across the universe might form a cosmic network of shared knowledge. Such a collective could potentially tackle questions that have puzzled humanity for centuries, such as the nature of dark matter, the origins of the universe, or the existence of other dimensions. This cosmic collaboration could accelerate our understanding of the universe at an unprecedented rate. Furthermore, collective intelligence might play a crucial role in the search for extraterrestrial life. By combining the observational capabilities and analytical power of multiple civilizations, we could greatly enhance our ability to detect and communicate with other intelligent life forms in the vast expanse of space. Artificial intelligence could play a significant role in our quest to understand and potentially fulfill cosmic purpose. As we develop more advanced AI systems, they may help us analyze vast amounts of astronomical data, identifying patterns and connections that human minds might overlook. This could lead to groundbreaking discoveries about the nature of our universe and our place within it. Furthermore, AI could assist in the search for extraterrestrial intelligence by sifting through complex signals from space and recognizing potential signs of alien civilizations. If we were to make contact with other intelligent life forms, AI might prove invaluable in decoding their messages and facilitating communication. On a more philosophical level, as artificial intelligence becomes more sophisticated, it might offer new perspectives on consciousness and the nature of intelligence itself. This could shed light on whether intelligence and consciousness are fundamental aspects of the universe, potentially aligning with theories of panpsychism or cosmic consciousness. Ultimately, if there is indeed a cosmic purpose to be fulfilled, artificial intelligence could become a powerful tool in humanity's arsenal, augmenting our cognitive abilities and helping us tackle the most profound questions about existence, purpose, and the ultimate fate of the universe. The ability to manipulate the environment is a crucial factor in determining intelligent life's cosmic significance. As species evolve and develop higher cognitive functions, they gain the capacity to alter their surroundings, which can have far-reaching implications for their planet and potentially beyond. Intelligent life forms that can manipulate their environment often progress through technological advancements. These advancements allow them to harness energy, develop tools, and eventually explore beyond their immediate surroundings. This exploration might lead to the colonization of other planets, or even the ability to detect and communicate with other intelligent civilizations across the cosmos. Furthermore, the impact of environmental manipulation extends to the potential for long-term survival and expansion. Intelligent species capable of modifying their habitat might be able to overcome planetary challenges such as climate change, resource depletion, or cosmic threats like asteroid impacts. This resilience could increase their chances of persisting over cosmic timescales and spreading their influence throughout the universe. However, the ability to manipulate the environment also comes with great responsibility. Intelligent life forms must balance progress with sustainability to avoid destroying their own habitats or causing irreversible damage to other ecosystems they encounter. The cosmic significance of intelligent life ultimately depends on how wisely they use their ability to shape the world around them. The search for extraterrestrial intelligence, often called SETI, is a profound endeavor that intertwines with our quest to understand cosmic purpose. This scientific pursuit goes beyond simply looking for alien life. It delves into fundamental questions about our place in the universe and the nature of intelligence itself. By scanning the cosmos for signs of advanced civilizations, we are essentially asking if we are alone in the universe. This question has deep philosophical implications. If we were to discover other intelligent life, it would suggest that the emergence of consciousness might be a common outcome of cosmic evolution rather than a rare accident. The methods used in SETI, such as analyzing radio signals from distant stars, also push the boundaries of our technological capabilities. These advancements, in turn, expand our understanding of the universe, potentially bringing us closer to grasping its underlying principles and any possible purpose. Moreover, the very act of searching for extraterrestrial intelligence reflects a human drive to find meaning and connection on a cosmic scale. Whether or not this search ultimately succeeds, it represents our species reaching out beyond our planet, seeking to understand our role in the grand cosmic narrative. The search for extraterrestrial intelligence, known as SETI, employs various sophisticated methods to scan the cosmos for signs of alien civilizations. Radio telescopes play a crucial role, listening for narrow-band signals that could indicate artificial transmissions from distant worlds. Optical SETI uses powerful telescopes to search for brief, intense laser pulses that advanced civilizations might use for communication or propulsion. More recent SETI efforts have expanded to include the hunt for technosignatures, such as the waste heat from alien megastructures or the chemical signatures of industrial pollution in exoplanet atmospheres. Some researchers even propose looking for signs of astroengineering, where an advanced civilization might alter its entire star system in detectable ways. While SETI has not yet found conclusive evidence of extraterrestrial intelligence, its methods reveal much about our universe. The very act of searching forces us to consider the nature of intelligence, technology, and our place in the cosmos. If SETI were to succeed, it would profoundly impact our understanding of life's prevalence and evolution. The methods used in SETI, even without detecting aliens, provide valuable data about stellar behavior, exoplanet composition, and the general structure of our galaxy. This information, combined with the philosophical implications of the search itself, offers intriguing clues about the potential purpose or nature of our universe, suggesting it might be a realm ripe for the emergence and evolution of intelligent life. The Drake equation stands as a pivotal tool in our quest to understand the potential for intelligent life beyond Earth. Developed by astronomer Frank Drake in 1961, this equation provides a framework for estimating the number of civilizations in our galaxy capable of communicating across the vast distances of space. At its core, the Drake equation considers several key factors that influence the emergence and survival of intelligent life. These include the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, and the likelihood of life evolving to intelligence. It also takes into account the longevity of technological civilizations, acknowledging that advanced societies must endure long enough to overlap in time for communication to occur. While the Drake equation does not provide a definitive answer, its true value lies in stimulating scientific discussion and guiding research. It highlights the critical areas we need to investigate to better understand our cosmic context. As we continue to discover exoplanets, study the conditions necessary for life, and search for biosignatures in distant atmospheres, we refine the variables in the equation. The significance of the Drake equation extends beyond mere numbers. It serves as a reminder of the immense possibilities that exist in our universe and encourages us to look beyond our own world. By framing the question of extraterrestrial intelligence in a systematic way, it has spurred advancements in astronomy, biology, and the emerging field of astrobiology, driving our exploration of the cosmos and our place within it. The Fermi paradox poses a profound challenge to our understanding of cosmic purpose and intelligent life by highlighting a striking contradiction. Given the vastness of the universe, with its billions of galaxies and countless potentially habitable planets, one might expect evidence of extraterrestrial civilizations to be abundant. Yet, we have not detected any clear signs of intelligent life beyond Earth. This absence of evidence forces us to confront several unsettling possibilities. Perhaps intelligent life is exceptionally rare, suggesting that our existence might be a cosmic fluke rather than part of a grand universal design. Alternatively, civilizations might consistently destroy themselves before achieving interstellar communication, implying a grim fate for technologically advanced species. The Fermi paradox also challenges our assumptions about the nature of intelligence and its cosmic role. If intelligent life is common but undetectable, we may need to reconsider our methods of searching for it or our understanding of how advanced civilizations behave. This could mean that intelligence does not inevitably lead to expansion and exploration, contrary to many of our expectations. Moreover, the paradox raises questions about the potential limitations of our own knowledge and perception. Are we simply unable to recognize signs of alien intelligence, or are we looking in the wrong places? These considerations compel us to expand our thinking about the forms that life and intelligence might take in the cosmos, pushing the boundaries of our imagination and scientific inquiry. Radio telescopes are crucial instruments in the search for extraterrestrial intelligence, often referred to as SETI. These massive dish-shaped antennas are designed to detect and collect radio waves from space, allowing scientists to listen for potential signals from alien civilizations. The search focuses on specific frequencies that scientists believe intelligent life might use for communication. One such frequency is the hydrogen line, which occurs at 1420 MHz. This frequency is significant because hydrogen is the most abundant element in the universe, and scientists speculate that any advanced civilization would be aware of its importance. Radio telescopes can scan vast areas of the sky, searching for unusual patterns or repetitions that might indicate an artificial origin. They are particularly useful because radio waves can travel enormous distances through space without significant degradation, making them an ideal medium for interstellar communication. Some of the largest radio telescopes involved in SETI include the Arecibo Observatory in Puerto Rico, which was operational until 2020, and the 500-meter Aperture Spherical Telescope in China. These powerful instruments continue to scan the cosmos, listening for that elusive signal that could change our understanding of our place in the universe. The search for techno-signatures, signs of advanced technology from extraterrestrial civilizations, could profoundly reshape our view of cosmic purpose. Detecting such signals would provide compelling evidence that we are not alone in the universe, suggesting that the emergence of intelligent life might be a more common outcome of cosmic evolution than previously thought. If we were to detect techno-signatures, it would imply that the universe has produced multiple instances of complex life capable of developing advanced technology. This discovery could indicate that the cosmos possesses an inherent tendency to generate conditions favorable for life and intelligence. It might suggest that the laws of physics and chemistry are fine-tuned not just for the existence of matter, but for the eventual emergence of conscious beings capable of understanding and manipulating their environment. Furthermore, the detection of techno-signatures could offer insights into the long-term survival and development of technological civilizations. If we find evidence of long-lived alien societies, it might indicate that intelligent life can overcome existential challenges and persist for extended periods. This could imply a cosmic purpose that extends beyond the mere existence of life, encompassing the growth, expansion, and possibly even the interconnection of intelligent species across vast distances. However, it is crucial to note that the absence of detectable techno-signatures does not necessarily negate the possibility of cosmic purpose. The universe might harbor forms of life or intelligence that are beyond our current ability to detect or comprehend. The quest for technosignatures ultimately drives us to explore fundamental questions about our place in the cosmos and the potential trajectories of intelligent life throughout the universe. Exoplanet atmospheres hold immense importance in our quest to find life and intelligence beyond Earth. These gaseous envelopes surrounding distant worlds provide crucial clues about the potential habitability of planets orbiting other stars. One key aspect scientists examine is the presence of biosignature gases in exoplanet atmospheres. These are molecules that, on Earth, are primarily produced by living organisms. Oxygen, for instance, is abundant in our atmosphere due to photosynthetic life. Detecting significant amounts of oxygen or methane in an exoplanet's atmosphere could indicate the presence of biological processes. The composition of an exoplanet's atmosphere also reveals information about its climate and surface conditions. This data helps researchers determine if a planet might have liquid water, a critical component for life as we know it. Additionally, atmospheric characteristics can hint at the presence of a magnetic field, which shields a planet from harmful radiation and helps retain its atmosphere. Advanced civilizations might also leave detectable traces in their planet's atmosphere. Pollutants or artificial compounds could potentially be identified, suggesting the existence of industrial activity. While such detection remains highly challenging with current technology, future advancements may bring us closer to discovering signs of extraterrestrial intelligence through atmospheric analysis. The galactic habitable zone is a region within our Milky Way galaxy where conditions are thought to be most favorable for the development of complex life. This concept plays a crucial role in the search for extraterrestrial intelligence by narrowing down the vast expanse of space to areas where intelligent life is more likely to exist. In the galactic habitable zone, stars are neither too close to the galactic center nor too far from it. This optimal distance provides a balance of essential elements needed for life, while also offering protection from harmful cosmic events. Closer to the galactic core, intense radiation and frequent supernova explosions could sterilize planets. Too far out, there might not be enough heavy elements to form rocky planets or support complex chemistry. Scientists focusing on the search for extraterrestrial intelligence often prioritize stars within this zone when looking for potential signals or habitable planets. The galactic habitable zone is estimated to be a ring-like region, located roughly 20,000 to 30,000 light-years from the galactic center. Our own solar system sits comfortably within this zone, supporting the idea that it could be a prime area for life to flourish. Understanding the galactic habitable zone helps researchers allocate resources more effectively in their search for extraterrestrial intelligence. By concentrating on stars and planets within this region, scientists can increase the chances of detecting signs of advanced civilizations or biosignatures that indicate the presence of life beyond Earth. Interstellar communication represents a profound frontier in our quest to understand our place in the cosmos and potentially uncover any overarching cosmic purpose. By reaching out beyond our solar system, we extend our search for meaning and connection to the vast expanse of the universe. The act of sending messages into space, such as the Arecibo message or the golden records aboard the Voyager spacecraft, reflects our innate desire to make contact and share our existence with potential alien civilizations. These efforts embody our hope that we are not alone in the universe and that there might be others out there pondering the same existential questions. Receiving a message from an extraterrestrial intelligence would be a transformative event for humanity. It could provide insights into how other beings perceive the universe, their understanding of physics, and their philosophical or spiritual beliefs. This exchange of knowledge might help us piece together a more comprehensive picture of cosmic reality and purpose. Moreover, the mere attempt at interstellar communication pushes the boundaries of our technological capabilities and scientific understanding. It forces us to grapple with concepts like the vastness of space, the nature of intelligence, and the fundamental laws of the universe. This pursuit itself might be seen as part of our cosmic purpose, driving us to explore, learn, and grow as a species. The Great Filter hypothesis offers a thought-provoking perspective on the apparent scarcity of intelligent life in our universe. This concept suggests that there are immense challenges or obstacles that civilizations must overcome to reach an advanced stage of development. These filters could occur at various points in a species' evolution, from the emergence of simple life to the development of complex intelligence and beyond. When we consider the vastness of the cosmos and the billions of potentially habitable planets, the absence of clear signs of extraterrestrial intelligence becomes particularly striking. The Great Filter hypothesis proposes that this absence might be due to the extreme difficulty of passing through all the necessary stages of development. It suggests that most life forms or civilizations fail to progress beyond certain critical points, explaining why we have not yet encountered other advanced species. This idea has profound implications for our understanding of cosmic purpose and the potential trajectory of intelligent life. If the Great Filter lies in our past, humanity may have already overcome the most significant hurdles to its existence and development. This could imply that we have a special role or responsibility in the cosmos as one of the few or possibly the only civilization to have made it this far. Conversely, if the Great Filter lies in our future, it could suggest that there are still major challenges ahead that threaten our long-term survival and progress. This perspective might imbue our actions and decisions with even greater significance, as they could determine whether we successfully navigate these future obstacles and fulfill a potential cosmic purpose of spreading intelligence throughout the universe. Time is a fundamental aspect of our universe, intricately woven into its very fabric. As we explore the cosmos, we find that time is not just a backdrop against which events unfold, but an active participant in the grand cosmic narrative. The flow of time shapes the evolution of stars, galaxies, and the universe itself, guiding the cosmic dance from the Big Bang to the present day and beyond. When we consider the potential purpose of the universe, time takes on even greater significance. The universe appears to be evolving, growing more complex and structured as time progresses. From the initial simplicity of the early universe, we now observe intricate systems and phenomena that have developed over billions of years. This progression suggests that time might be a crucial factor in whatever purpose the universe might serve. Some scientists speculate that the universe could be a vast computational system, with time serving as the mechanism by which information is processed and complexity increases. Others propose that the arrow of time, always moving forward, drives the universe towards some unknown goal or state of maximum entropy. These ideas, while speculative, highlight how our understanding of time shapes our perception of the universe's potential purpose. Ultimately, the relationship between time and the universe's purpose remains one of the greatest mysteries in cosmology. As we continue to study the cosmos, we may uncover new insights into how time influences the grand design of the universe, potentially revealing clues about its ultimate fate and any overarching purpose it might possess. The arrow of time is a fundamental concept in our understanding of cosmic evolution, pointing to the unidirectional flow of events from past to future. This irreversibility is deeply woven into the fabric of our universe, shaping its development from the earliest moments after the Big Bang to the present day and beyond. In the context of cosmic evolution, the arrow of time manifests in several key ways. The expansion of the universe itself is a prime example, as space continues to stretch outward, driving galaxies farther apart. This expansion is not simply a reversal of a previous contraction, but a one-way process that defines the large-scale evolution of the cosmos. The arrow of time is also evident in the formation and evolution of cosmic structures. Gravity pulls matter together, leading to the creation of stars, galaxies, and galaxy clusters. These processes increase the complexity and organization of matter in the universe, another hallmark of time's arrow. Stars form, live out their lives, and die, irreversibly changing the composition of the universe by producing heavier elements. Perhaps most intriguingly, the arrow of time is linked to the concept of entropy, a measure of disorder in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This principle underlies many aspects of cosmic evolution, from the cooling of the early universe to the eventual heat-death scenario billions of years in the future. The arrow of time thus serves as a cosmic guidepost directing the unfolding story of our universe. Entropy plays a crucial role in shaping the universe's evolution and might offer insights into its potential purpose. As a fundamental concept in thermodynamics, entropy measures the degree of disorder or randomness in a system. In the context of the universe, entropy continually increases over time, driving the cosmos towards a state of maximum disorder. This inexorable march towards higher entropy has profound implications for the universe's evolution. It explains why time appears to flow in one direction and why certain processes, like the mixing of hot and cold water, are irreversible. The increase in entropy also accounts for the gradual cooling and expansion of the universe since the Big Bang. Some scientists speculate that the universe's purpose, if it has one, might be tied to entropy. The idea of a cosmic heat death suggests that the universe will eventually reach a state of maximum entropy, where all energy is evenly distributed and no further work can be done. This ultimate fate raises questions about the meaning and purpose of existence itself. However, it is important to note that entropy does not preclude the formation of complex structures or life. In fact, localized decreases in entropy can occur within larger systems that are increasing in overall entropy. This phenomenon allows for the emergence of ordered structures like galaxies, stars, and even living organisms, adding another layer of complexity to our understanding of the universe's evolution and potential purpose. Cosmic expansion is a fundamental force shaping the universe's timeline, driving the continuous growth of space itself. This expansion, first observed by Edwin Hubble in the 1920s, causes galaxies to move away from each other at ever-increasing speeds. As the universe expands, it cools and becomes less dense. This cooling process has marked distinct eras in cosmic history. In its earliest moments, the universe was incredibly hot and dense. As it expanded, it cooled enough for particles to form, then atoms, and eventually stars and galaxies. The rate of expansion also influences the fate of the universe. If expansion continues to accelerate, as current observations suggest, the universe might face a big freeze, where stars burn out and matter becomes increasingly isolated. This expansion even affects the visibility of distant objects, as some galaxies are now moving away from us faster than their light can travel toward us. Understanding cosmic expansion is crucial for cosmologists studying the age, composition, and ultimate destiny of our universe. It provides a framework for interpreting observations of distant galaxies and the cosmic microwave background, offering insights into the universe's past and potential future. Cyclic models of the universe propose that our cosmos undergoes endless cycles of expansion and contraction rather than having a singular beginning or end. This concept challenges the idea of a universe with a definitive purpose or goal, suggesting instead that existence itself might be the fundamental nature of reality. In these models, each cycle of the universe could be seen as an opportunity for different configurations of matter and energy to arise, potentially allowing for countless variations of physical laws and structures. This vast array of possibilities might lead to the emergence of complexity and even life in some cycles, while others remain barren. The cyclical nature of these models also raises intriguing questions about the accumulation of information or patterns across cycles. Some theories suggest that certain fundamental aspects might carry over from one cycle to the next, potentially allowing for a form of cosmic evolution or refinement over immense timescales. Ultimately, cyclic models of the universe invite us to consider purpose not as an end goal, but as an ongoing process of existence, change, and renewal. They challenge us to expand our understanding of cosmic significance beyond linear narratives and to embrace the possibility of a universe that simply is, perpetually reinventing itself through endless cycles of creation and destruction. Cosmic epochs serve as crucial milestones in our understanding of the universe's evolution. These distinct periods mark significant changes in the cosmos, helping scientists track the universe's development from its earliest moments to the present day. The study of cosmic epochs reveals how the universe transformed over time. In the earliest epoch, just after the Big Bang, the universe was incredibly hot and dense. As it expanded and cooled, it entered new phases, each characterized by unique conditions and events. For instance, the formation of the first atoms, the emergence of stars and galaxies, and the acceleration of cosmic expansion all define different epochs. These epochs provide a framework for understanding complex astrophysical processes. By examining each period, scientists can piece together the cosmic puzzle, connecting cause and effect across billions of years. This knowledge not only helps explain the universe we see today, but also allows us to make predictions about its future. Moreover, cosmic epochs highlight the interconnectedness of cosmic phenomena. Events in one epoch often set the stage for developments in the next, creating a continuous narrative of cosmic evolution. This perspective enriches our appreciation of the universe's history and our place within it. The concept of heat death offers a sobering perspective on the universe's long-term trajectory. As entropy increases over vast timescales, the universe gradually moves towards a state of maximum disorder. In this scenario, all energy becomes evenly distributed, and no work can be performed. Stars exhaust their fuel, black holes eventually evaporate, and even the smallest particles decay. This relentless march towards uniformity raises profound questions about cosmic purpose. If the universe is destined for a state where nothing meaningful can occur, what significance can we attribute to its existence? Some argue that the heat death represents the ultimate futility of all processes in the universe, rendering any notion of cosmic purpose meaningless. However, others view this concept differently. They suggest that the very existence of complex structures and life forms in the present moment gives the universe meaning, regardless of its final state. The fact that we can contemplate these ideas and seek understanding might itself be seen as a form of purpose, albeit a temporary one. Moreover, our current understanding of physics may be incomplete. Future discoveries could reveal mechanisms that prevent heat death or introduce new concepts of cosmic evolution. The quest to unravel these mysteries and comprehend our place in the cosmos continues to drive scientific exploration and philosophical inquiry. Time dilation and relativity fundamentally reshape our understanding of cosmic timescales, revealing that time itself is not a constant but a flexible dimension influenced by gravity and motion. This concept, central to Einstein's theory of relativity, shows that time passes differently depending on an object's speed or its proximity to massive bodies. In the cosmic arena, these effects become pronounced. Near black holes, where gravity is incredibly strong, time slows dramatically compared to regions of weaker gravity. This means that events unfolding near a black hole's event horizon might appear to take eons from our perspective on Earth, while only moments pass for an observer close to the black hole. Relativity also impacts our observations of the early universe. The light we see from distant galaxies has traveled for billions of years, affected by the expansion of space itself. This stretching of light, known as cosmological redshift, provides crucial information about the age and evolution of the universe, allowing scientists to peer back almost to the moment of the Big Bang. These relativistic effects challenge our intuitive notions of time and space, forcing us to reconsider how we measure and interpret cosmic events. They reveal a universe far more complex and interconnected than classical physics suggested, where time and space are woven into a single, dynamic fabric of reality. Eternal inflation proposes that our universe is just one of countless bubbles in an ever-expanding cosmic foam. This theory suggests that the process of inflation, which rapidly expanded our universe in its earliest moments, never truly ends. Instead, it continues indefinitely, creating new bubble universes with potentially different physical laws and properties. In terms of the universe's purpose, eternal inflation challenges the notion of a singular, predetermined goal. If infinite universes are constantly forming, each with its own unique characteristics, it becomes difficult to ascribe a single overarching purpose to the entire multiverse. Instead, the concept invites us to consider that purpose and meaning might be localized within each universe, or even created by the conscious beings that emerge within them. Regarding the timeline of the universe, eternal inflation dramatically alters our perspective. Rather than a linear progression from the Big Bang to a potential end, we must consider a vast, possibly infinite expanse of time in which new universes are continually born. Our own universe's timeline becomes just one thread in an immense cosmic tapestry, with no clear beginning or end to the entire process. This view of the cosmos raises profound questions about the nature of existence and our place within it. It suggests that the story of our universe, rather than being unique, might be one of countless cosmic narratives unfolding across an unimaginably vast multiverse. Cosmic microwave background radiation serves as a powerful tool for understanding the early universe and its evolution. This faint glow, permeating all of space, is essentially the afterglow of the Big Bang, providing us with a snapshot of the universe when it was merely 380,000 years old. By studying the subtle variations in temperature and polarization of this radiation, scientists can glean crucial information about the composition and structure of the early universe. These minute fluctuations, only about 1 part in 100,000, represent the seeds of cosmic structure, eventually leading to the formation of galaxies, stars, and planets we observe today. The cosmic microwave background also provides strong evidence for the inflationary model of the early universe, suggesting a period of rapid expansion shortly after the Big Bang. This expansion helps explain the remarkable uniformity of the radiation across the sky and the flatness of space on large scales. While the cosmic microwave background offers invaluable insights into the history and evolution of the universe, it does not directly address questions of purpose. Science can describe how the universe works and has changed over time, but questions of ultimate purpose or meaning extend beyond the realm of empirical observation and into philosophy and personal belief. The concept of information provides a fascinating lens through which we can examine the potential purpose of the universe. At its core, information is about patterns, structures, and relationships between different elements. In the context of the cosmos, we can think of the universe itself as a vast repository of information. Some scientists propose that the fundamental nature of reality might be information itself. This idea suggests that the universe could be seen as a cosmic computer, processing and storing information through its very existence. The laws of physics, in this view, are not just descriptions of how the universe behaves, but are themselves information encoded into the fabric of reality. This perspective opens up intriguing possibilities about the purpose of the universe. If information is indeed fundamental, one could argue that the universe exists to create, process, and perhaps even understand information. The emergence of complex structures, from galaxies to living organisms, could be seen as the universe's way of generating increasingly sophisticated forms of information processing. Moreover, the concept of information ties into questions of consciousness and intelligence. As the only known entities capable of consciously interpreting and manipulating information, intelligent beings like humans might play a crucial role in the universe's information processing. This raises profound questions about our place in the cosmos and whether the development of intelligence could be one of the underlying purposes of the universe itself. Complexity plays a crucial role in cosmic evolution, shaping the universe from its simplest beginnings to the intricate systems we observe today. As the cosmos expanded and cooled after the Big Bang, it allowed for the formation of increasingly complex structures. This process began with the emergence of fundamental particles, which combined to form atoms, then molecules, and eventually the diverse array of celestial objects we see in the night sky. The evolution of complexity in the universe is not just a matter of increasing size or number, but of emerging properties and behaviors. For instance, when atoms came together to form the first stars, these cosmic furnaces began producing heavier elements through nuclear fusion. These new elements, in turn, enabled the formation of even more complex structures, including planets, moons, and eventually, life itself. Some scientists propose that the increase in cosmic complexity might hint at a potential purpose or direction in the universe's evolution. This idea, sometimes called the cosmic evolutionary synthesis, suggests that the universe may have an inherent tendency to produce ever more complex and organized systems over time. However, it is important to note that this concept remains speculative and is not universally accepted in the scientific community. The role of complexity in cosmic evolution raises profound questions about the nature of our universe and our place within it. As we continue to explore and understand these intricate cosmic processes, we may gain new insights into the fundamental workings of reality and perhaps even glimpse the underlying principles that govern the cosmos. The emergence of complex systems in our universe raises intriguing questions about purpose and order. As we observe the cosmos, we see patterns of increasing complexity, from the formation of atoms to the birth of stars, galaxies, and eventually life itself. This progression from simplicity to complexity occurs through natural processes, guided by the fundamental laws of physics. While these systems arise spontaneously, they exhibit remarkable organization and efficiency. Take, for example, the intricate dance of ecosystems or the precise interactions within living cells. These complex systems demonstrate a level of sophistication that can appear purposeful, even in the absence of a conscious designer. Some scientists and philosophers argue that this tendency towards complexity and organization suggests an inherent drive or direction in the universe. They propose that the cosmos might have an innate propensity to create ever more intricate structures and relationships. This idea challenges us to consider whether purpose can emerge from unpurposed beginnings. However, it is crucial to note that the appearance of purpose does not necessarily imply intent. The emergence of complex systems can be explained through natural selection, self-organization, and the laws of physics without invoking a universal purpose. The debate continues, inviting us to ponder the nature of our universe and our place within it. Self-organizing systems play a crucial role in cosmic evolution, driving the formation and development of complex structures throughout the universe. These systems emerge spontaneously from simpler components, creating order and patterns without external guidance. In the context of cosmic evolution, this process is fundamental to understanding how the universe has transformed from its initial, nearly uniform state after the Big Bang to the rich tapestry of galaxies, stars, and planets we observe today. On the largest scales, self-organization manifests in the cosmic web, a vast network of dark matter filaments and galaxy clusters that formed as a result of gravitational interactions. This intricate structure arose naturally from tiny fluctuations in the early universe, growing over billions of years into the complex cosmic architecture we see now. At smaller scales, self-organization is evident in the formation of stars and planetary systems. Vast clouds of gas and dust collapse under their own gravity, forming dense regions that eventually ignite as stars. The leftover material often coalesces into planets, moons, and asteroids, creating solar systems through a process of accretion and gravitational dynamics. Even in the realm of biology, self-organization is a key factor in the emergence of life and its subsequent evolution. The ability of complex organic molecules to form and interact in ways that lead to self-replicating systems is a prime example of self-organization at work in the cosmic story. This process highlights how the principles of self-organization span from the grandest cosmic scales down to the microscopic world of living organisms. Emergence plays a crucial role in our understanding of cosmic structures and their development. This concept describes how complex systems and patterns arise from relatively simple interactions. In the context of the universe, emergence helps explain how the intricate cosmic web we observe today evolved from the nearly uniform conditions after the Big Bang. The formation of galaxies, stars, and planets can all be viewed through the lens of emergence. Tiny quantum fluctuations in the early universe grew over time due to gravity, eventually leading to the vast cosmic structures we see today. These structures, from galaxy clusters to individual solar systems, exhibit properties and behaviors that could not have been predicted by simply studying their constituent parts in isolation. Emergence also relates to the potential for purpose or meaning in the cosmos. As increasingly complex systems develop, new properties and capabilities arise. For instance, the emergence of life on Earth introduced the possibility of conscious observation and exploration of the universe. This raises intriguing questions about whether the universe itself might develop emergent properties on a cosmic scale, potentially leading to forms of complexity or consciousness beyond our current comprehension. While emergence does not necessarily imply a predetermined purpose for the universe, it does suggest that the cosmos has the potential to generate increasingly sophisticated structures and phenomena. This concept encourages us to consider the possibility that the universe may still be evolving towards states of greater complexity, with unforeseen emergent properties yet to arise. Entropy is a fundamental concept in the universe, shaping the creation and destruction of complex systems on all scales. At its core, entropy represents the tendency of energy to spread out and become more disordered over time. This principle drives the formation and eventual decay of everything from stars and galaxies to living organisms and human societies. In the creation of complex systems, entropy plays a counterintuitive role. While the overall entropy of the universe increases, local pockets of decreased entropy can form, allowing for the emergence of organized structures. This occurs when energy flows through a system, temporarily creating order amidst the larger trend of disorder. For instance, the formation of stars and planets represents a local decrease in entropy, as matter coalesces and organizes under the influence of gravity. However, entropy ultimately leads to the destruction of these same complex systems. As energy continues to spread out and become more evenly distributed, organized structures break down. Stars exhaust their fuel and die, planets cool and become geologically inactive, and even the largest cosmic structures will eventually succumb to the relentless march of entropy. The interplay between entropy and complexity is particularly evident in living systems. Life itself can be seen as a temporary defiance of entropy, maintaining order through constant energy input. Yet, this process is not sustainable indefinitely, and the eventual breakdown of living systems is an inevitable consequence of entropy's inexorable influence. Information theory offers intriguing insights into our quest to understand cosmic purpose. This mathematical framework, which deals with the quantification, storage, and communication of information, has far-reaching implications for how we perceive the universe and its potential meaning. One key concept from information theory is entropy, which measures the amount of disorder or randomness in a system. When applied to the cosmos, this idea suggests that the universe tends towards increasing complexity and information content over time. From the relative simplicity of the early universe to the intricate structures we see today, This progression might hint at a fundamental drive towards greater organization and complexity. Another relevant aspect is the idea of information preservation. Some physicists propose that information cannot be truly destroyed, even in extreme cosmic events like black holes. This concept of information conservation could imply a deeper significance to the patterns and structures we observe in the universe, potentially pointing towards an overarching purpose or meaning. Furthermore, information theory provides a framework for understanding how complex systems, including life itself, can emerge from simpler components. This perspective suggests that the development of consciousness and intelligence might be an inherent tendency of the cosmos rather than a random occurrence. Such a view could align with the idea of a universe that is, in some sense, purposeful or goal-oriented. Fractal patterns are a remarkable phenomenon that appears throughout nature and the cosmos, revealing an underlying order in seemingly chaotic systems. These self-similar structures, which repeat at different scales, can be found in the branching of trees, the formation of snowflakes, and even the distribution of galaxies in the universe. In nature, fractals often emerge as efficient solutions to complex problems. The branching structure of our lungs, for example, maximizes surface area for gas exchange while minimizing the space occupied. Similarly, the fractal structure of coastlines allows for the most efficient interface between land and sea. On a cosmic scale, fractal patterns are evident in the large-scale structure of the universe. Galaxy clusters and superclusters form a web-like network that resembles the neurons in our brains or the mycelial networks of fungi. This similarity across vastly different scales suggests a fundamental principle of organization in the cosmos. The prevalence of fractals in nature and the universe points to an important connection between mathematics and physical reality. It suggests that simple rules can give rise to complex structures and that there may be underlying principles governing the formation and growth of systems across all scales. This realization has profound implications for our understanding of the universe and our place within it. The holographic universe theory proposes that our entire cosmos might be akin to a vast, three-dimensional projection emanating from a two-dimensional surface. This concept draws parallels with how a hologram creates the illusion of depth from a flat image. In this framework, information plays a crucial role, as it suggests that all the data about our universe could be encoded on its outermost boundary, much like information on a computer hard drive. This theory has profound implications for our understanding of reality and cosmic purpose. It suggests that what we perceive as physical reality might be an intricate interplay of information, challenging our conventional notions of space, time, and matter. The holographic principle implies that the universe operates like a cosmic computer, processing and storing information in ways we are only beginning to comprehend. From this perspective, the purpose of the cosmos might be intrinsically tied to the creation, manipulation, and preservation of information. Every event, from the collision of galaxies to the thoughts in our minds, could be seen as part of an immense informational tapestry. This view aligns with recent developments in quantum physics and information theory, hinting at a deep connection between the fabric of reality and the nature of information itself. The holographic universe theory also raises intriguing questions about consciousness and our role in the cosmos. If reality is fundamentally informational, our conscious experiences might be integral to the universe's information processing capabilities. This idea opens up new avenues for exploring the relationship between mind, matter, and the underlying structure of the universe, potentially revealing hidden dimensions of cosmic purpose and meaning. Quantum information is a fundamental aspect of our universe, playing a crucial role in shaping its structure and potentially influencing its purpose. At the smallest scales, the universe operates according to the principles of quantum mechanics, where information is encoded in the quantum states of particles and systems. This quantum information forms the basis for all matter and energy in the cosmos. It determines how particles interact, combine, and evolve, ultimately giving rise to the complex structures we observe, from atoms and molecules to stars and galaxies. The quantum nature of information allows for phenomena like superposition and entanglement, which are essential for understanding the behavior of matter and energy at the most fundamental levels. Some scientists propose that the universe itself might be a vast quantum computer, processing information at an unimaginable scale. This perspective suggests that the very fabric of space-time could be composed of quantum bits or qubits, constantly computing and evolving. If true, this would imply that the structure and evolution of the universe are intrinsically linked to the processing of quantum information. Furthermore, the concept of quantum information has led to intriguing theories about the nature of black holes and the holographic principle, which posits that all the information in our three-dimensional universe might be encoded on a two-dimensional surface, much like a hologram. These ideas highlight the profound connection between information, quantum mechanics, and the structure of the cosmos, hinting at a deeper purpose or organizing principle underlying the universe as we know it. The anthropic principle is a concept in cosmology that addresses the apparent fine-tuning of the universe for the existence of life. It suggests that the fundamental constants and laws of physics seem precisely calibrated to allow for the emergence of complex structures, including living organisms. This observation has led to discussions about whether our universe is uniquely suited for life, or if there might be a multitude of universes with different properties. When considering the anthropic principle, scientists often point to examples such as the strength of gravity, the ratio of electromagnetic forces to nuclear forces, and the balance between matter and antimatter. If any of these parameters were slightly different, the universe as we know it might not exist, and life might not have been possible. The anthropic principle relates to the idea of cosmic purpose by raising questions about the nature of our existence and our place in the universe. Some interpret the apparent fine-tuning as evidence of a purposeful design, suggesting that the universe was created with the intention of supporting life. Others view it as a selection effect, arguing that we naturally find ourselves in a universe capable of supporting our existence, regardless of whether it was designed for that purpose. This concept challenges us to consider whether the universe has an inherent purpose or if our existence is simply a consequence of the particular conditions that happen to arise. It invites us to ponder the possibility of other universes with different properties and whether life could exist in forms we cannot yet imagine. The anthropic principle thus serves as a bridge between scientific inquiry and philosophical contemplation about our cosmic significance. The concept of fine-tuning in physics refers to the observation that many fundamental constants and physical laws appear to be precisely calibrated to allow for the existence of life as we know it. This delicate balance has led some scientists and philosophers to ponder whether our universe might have a purpose or design. Consider the strength of gravity, for example. If it were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars would not form at all. Similarly, the strong nuclear force that binds quarks together must be within a narrow range to allow for the formation of stable atoms. This apparent fine-tuning has sparked debate about its implications. Some argue that it suggests an intentional design, pointing to a potential cosmic purpose or even a creator. Others propose the multiverse theory, suggesting our universe is one of many, and we simply happen to exist in one with conditions suitable for life. Critics of the fine-tuning argument contend that it may be a result of observational bias. They argue that we can only observe a universe capable of supporting our existence, so it's not surprising that we find ourselves in one that appears fine-tuned. Regardless of the interpretation, the concept of fine-tuning continues to fuel scientific inquiry and philosophical discussions about the nature and potential purpose of our universe. The anthropic principle is a fascinating concept in cosmology that attempts to explain the apparent fine-tuning of our universe. There are several interpretations, each offering a unique perspective on our place in the cosmos. The weak anthropic principle simply states that the universe must have properties that allow life to exist, as we are here to observe it. This interpretation doesn't imply any cosmic purpose, but rather points out that our existence naturally selects for a universe capable of supporting life. The strong anthropic principle takes a bolder stance, suggesting that the universe must have properties that allow life to develop at some point in its history. This interpretation hints at a potential cosmic purpose, as it implies that the emergence of life might be an inherent feature of our universe. Some scientists propose a multiverse interpretation, where our universe is just one of many with different physical constants. In this view, we naturally find ourselves in a universe capable of supporting life, while countless others may not. This interpretation doesn't necessarily imply a cosmic purpose, but rather explains our existence through probability across multiple universes. The multiverse theory and the anthropic principle intertwine in fascinating ways, offering potential explanations for our universe's apparent fine-tuning. According to the multiverse concept, our universe is just one of countless others, each with its own unique set of physical laws and constants. This vast array of universes provides a framework for understanding the anthropic principle, which suggests that the conditions in our universe appear perfectly suited for life because we exist to observe them. In this context, the multiverse theory posits that among the immense number of universes, some will inevitably have the right conditions for life to emerge. Our universe happens to be one of these life-supporting realms, which is why we find ourselves in a cosmos that seems tailor-made for our existence. This perspective shifts the question from why our universe is so precisely tuned for life to why we should expect to find ourselves in a universe capable of supporting our existence. The concept of cosmic purpose takes on new dimensions when viewed through the lens of the multiverse and anthropic principle. Rather than suggesting a predetermined design or intent for the cosmos, these ideas point to a more probabilistic view of our existence. The apparent purpose or meaning we perceive in our universe may be a natural consequence of the vast possibilities inherent in a multiverse, where every conceivable combination of physical laws and constants can potentially exist. This interconnection between the multiverse theory, anthropic principle, and notions of cosmic purpose challenges us to reconsider our place in the cosmos. It invites us to contemplate the extraordinary circumstances that allow for our existence while acknowledging the possibility of countless other universes where different forms of life or no life at all might exist. Fundamental constants are the bedrock of our universe's physical laws. These unchanging values, such as the speed of light, the gravitational constant, and the charge of an electron, define how the cosmos operates. In the context of the fine-tuning argument, these constants take center stage, as their precise values appear crucial for the existence of a universe capable of supporting life as we know it. The fine-tuning argument posits that if these fundamental constants were even slightly different, our universe would be radically altered. For instance, if the strong nuclear force were marginally weaker, atoms could not hold together, and if it were slightly stronger, stars could not form. Similarly, a small change in the gravitational constant could lead to a universe that either expands too rapidly for galaxies to form or collapses back in on itself before life has a chance to emerge. This apparent precision in the values of fundamental constants has led some to argue that our universe must be the product of intelligent design. Others suggest that we might live in a multiverse where countless universes exist with different fundamental constants, and we simply happen to inhabit one suitable for life. Still others argue that there may be underlying physical principles we have yet to discover that necessitate these specific values. The role of fundamental constants in the fine-tuning argument continues to spark debate among physicists, philosophers, and theologians. It raises profound questions about the nature of our universe, the possibility of other universes, and our place within the cosmos. As we continue to explore and understand these constants better, we may gain new insights into the fundamental nature of reality itself. Observer selection bias and the anthropic principle are closely linked concepts in cosmology and philosophy of science. Observer selection bias refers to the tendency to draw conclusions based on the fact that we, as observers, exist to make those observations. This bias can lead us to overestimate the likelihood of conditions necessary for our existence. The anthropic principle, on the other hand, states that our observations of the universe must be compatible with the existence of conscious observers like ourselves. It suggests that the very fact we are here to observe the universe places constraints on what we can observe. These concepts intersect when we consider the apparent fine-tuning of our universe. Many physical constants and laws seem precisely calibrated to allow for the existence of complex life. Observer selection bias cautions us against assuming this fine-tuning is extraordinary, as we could only exist in a universe capable of supporting us. The anthropic principle further suggests that out of all possible universes, we necessarily find ourselves in one compatible with our existence. Understanding these concepts helps us navigate questions about the nature of our universe and our place within it. They remind us to consider the limitations and potential biases in our observations, encouraging a more nuanced approach to cosmological theories and interpretations of scientific data. Habitable zones play a crucial role in our understanding of the anthropic principle, which suggests that the universe must have properties that allow life to exist. These zones, often called Goldilocks zones, are regions around stars where conditions are just right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. The existence of habitable zones ties directly into the anthropic principle by highlighting the delicate balance of conditions necessary for life. Our own solar system demonstrates this perfectly, with Earth situated in the habitable zone of our Sun. This position allows for the presence of liquid water and a stable climate, factors that have been essential for the development and sustenance of life on our planet. The study of habitable zones in other star systems has profound implications for the anthropic principle. As we discover more exoplanets within the habitable zones of their stars, we gain insight into the potential prevalence of life-supporting environments in the universe. This knowledge informs our understanding of how common or rare the conditions for life might be, directly addressing core questions posed by the anthropic principle. Furthermore, the concept of habitable zones extends beyond individual star systems to a galactic scale. The galactic habitable zone refers to regions within a galaxy where conditions are favorable for the formation of complex life. This broader perspective aligns with the anthropic principle by suggesting that our existence might be tied not only to our local stellar environment, but also to our position within the Milky Way galaxy. The rare Earth hypothesis and cosmic fine-tuning are interconnected concepts that explore the unique conditions necessary for life as we know it to exist. The rare Earth hypothesis suggests that the specific combination of factors required for complex life to develop on Earth might be exceptionally uncommon in the universe. This idea aligns closely with the concept of cosmic fine-tuning, which proposes that the fundamental constants and laws of physics in our universe appear to be precisely calibrated to allow for the existence of life. Cosmic fine-tuning examines the delicate balance of physical constants, such as the strength of gravity, the mass of elementary particles, and the rate of expansion of the universe. If any of these constants were slightly different, the universe as we know it might not exist, let alone support life. The rare Earth hypothesis takes this concept further by considering the specific conditions on our planet that have allowed complex life to flourish. These conditions include Earth's position in the habitable zone of our solar system, the presence of a large moon stabilizing our planet's axis, the protective magnetic field shielding us from harmful radiation, and the unique composition of our atmosphere. The rare Earth hypothesis suggests that the combination of these factors might be extremely uncommon, potentially making Earth-like planets capable of supporting complex life quite rare in the universe. Both concepts challenge us to consider our place in the cosmos and the likelihood of finding other intelligent life. While they do not definitively prove that Earth is unique, they highlight the extraordinary set of circumstances that have allowed life to thrive on our planet, encouraging us to appreciate the delicate balance that sustains our existence in the vast expanse of the universe. The cosmological constant problem is a central issue in discussions of fine-tuning in the universe. This problem arises from the vast discrepancy between theoretical predictions and observational evidence regarding the energy density of empty space. Quantum field theory suggests that empty space should be teeming with energy from virtual particles popping in and out of existence. The predicted value for this vacuum energy is enormous, so large that it should cause the universe to expand at an incredible rate or even tear itself apart. However, astronomical observations show that the actual expansion of the universe is much slower, implying a vacuum energy density that is tiny in comparison to theoretical expectations. This enormous mismatch between theory and observation, spanning over 100 orders of magnitude, is what physicists call the cosmological constant problem. It plays a crucial role in fine-tuning debates because it suggests that some mechanism must be at work to cancel out the majority of the vacuum energy, leaving just the right amount for the universe as we know it to exist. Proponents of fine-tuning arguments often point to the cosmological constant problem as evidence that the universe appears to be carefully calibrated to allow for the existence of complex structures and life. They argue that even a slightly different value for the vacuum energy would result in a universe inhospitable to life, making our existence seem improbable without some form of fine-tuning. The anthropic principle plays a crucial role in shaping our approach to the search for extraterrestrial life. This concept suggests that the universe must have properties that allow for the existence of observers like ourselves. When applied to the quest for alien life, it prompts us to consider the conditions necessary for life as we know it to emerge and thrive. Our understanding of life is inherently biased by our own existence. We evolved on Earth, so we naturally look for environments similar to our own when searching for extraterrestrial life. This Earth-centric view leads us to focus on planets with liquid water, moderate temperatures, and atmospheres containing oxygen and other familiar elements. However, the anthropic principle also encourages us to broaden our perspective. It reminds us that the universe might support forms of life vastly different from our own. This realization has led scientists to explore the possibility of life in extreme environments, such as the methane lakes of Titan or the subsurface oceans of icy moons like Europa and Enceladus. The principle also influences our expectations about the frequency of life in the universe. If intelligent life is rare, then we might be among the first civilizations to emerge, explaining why we have not yet detected signs of others. Conversely, if life is common, we must question why we have not found evidence of it, leading to discussions about the potential hurdles civilizations face in their development and longevity. Theories of cosmic cycles offer intriguing perspectives on the potential purpose of the universe. These ideas suggest that our universe might be part of a larger, repeating pattern of creation and destruction. Some models propose that universes are born, expand, and eventually collapse, only to be reborn in a new cycle. This concept of cosmic renewal aligns with ancient philosophical ideas of eternal return found in various cultures. The cyclical nature of these theories hints at a universe that continually renews itself, potentially allowing for infinite possibilities and variations. This endless cycle of rebirth could be seen as a cosmic laboratory, where different physical laws and constants are tested in each iteration. From this viewpoint, the purpose of our universe might be to explore one set of possibilities among countless others. Furthermore, cosmic cycle theories challenge our understanding of time and causality. If the universe repeats endlessly, questions about its ultimate origin or final fate become less relevant. Instead, the focus shifts to the patterns and variations that emerge across cycles. This perspective suggests that the purpose of the universe might not be a singular goal, but rather an ongoing process of exploration and evolution. These theories also raise profound questions about the nature of existence and consciousness. If cosmic cycles are real, it implies that every possible configuration of matter and energy might eventually repeat. This concept touches on deep philosophical issues about identity, free will, and the nature of reality itself, further expanding our contemplation of the universe's potential purpose. Stellar life cycles are the engines of cosmic renewal, driving the evolution and transformation of the universe. Stars begin their lives as vast clouds of hydrogen and helium, collapsing under their own gravity to ignite nuclear fusion in their cores. This process not only generates the light and heat that sustains life on planets like Earth, but also creates heavier elements essential for the formation of complex structures in the cosmos. As stars age, they undergo different fates depending on their mass. Smaller stars like our Sun will eventually expand into red giants before shedding their outer layers, leaving behind a dense core known as a white dwarf. More massive stars experience a more dramatic end, exploding as supernovae. These cosmic explosions scatter newly forged elements across space, enriching the interstellar medium with the building blocks for future stars, planets, and even life itself. This cycle of stellar birth, life, and death is crucial for the ongoing evolution of the universe. Each generation of stars produces and distributes more heavy elements, gradually increasing the complexity and diversity of cosmic structures. The material ejected from dying stars becomes the raw ingredients for new star systems, planets, and potentially habitable worlds. The stellar life cycle thus represents a cosmic recycling system where nothing is truly lost, but rather transformed and repurposed. This process of renewal ensures that the universe remains dynamic and ever-changing, continually creating the conditions necessary for the emergence of new phenomena and potentially even life itself in the vast expanse of space. Galactic evolution plays a crucial role in our understanding of cosmic cycles, revealing the dynamic nature of the universe. As galaxies form, grow, and change over billions of years, they participate in a grand cycle of matter and energy transformation. Stars within galaxies are born from vast clouds of gas and dust, fusing lighter elements into heavier ones throughout their lifetimes. When these stars die, they release these newly created elements back into space, enriching the galactic environment. This process of stellar birth, life, and death repeats, gradually increasing the abundance of heavy elements in the universe over time. Galaxies themselves undergo cycles of mergers and interactions. Smaller galaxies collide and combine to form larger ones, while large galaxies cannibalize their smaller neighbors. These cosmic collisions trigger bursts of star formation, accelerating the cycle of stellar evolution and element production. Over vast timescales, this process leads to the formation of massive elliptical galaxies, which eventually cease star formation as they exhaust their gas supplies. The concept of galactic evolution extends beyond individual galaxies to the large-scale structure of the universe. Galaxies cluster together, forming immense cosmic webs separated by vast voids. This structure evolves over time, with matter flowing along filaments and collecting in dense nodes. By studying galactic evolution, scientists gain insights into the broader cycles of growth, transformation, and renewal that shape our cosmos, connecting the smallest scales of stellar formation to the grandest scales of universal structure. Black holes serve as cosmic recyclers, playing a crucial role in the ongoing evolution of the universe. These enigmatic objects consume matter, energy, and even light that ventures too close, pulling everything into their immense gravitational grasp. However, this process is not merely destructive, it's transformative. As material spirals into a black hole, it forms an accretion disk, heating up to extreme temperatures and emitting powerful radiation. This energy output can influence star formation and galactic evolution in surrounding regions. Some black holes also eject powerful jets of particles and energy, which can travel vast distances and interact with intergalactic matter. Supermassive black holes at the centers of galaxies are particularly important in this cosmic recycling process. They regulate the growth of their host galaxies by controlling the inflow and outflow of matter and energy. This feedback mechanism helps maintain a balance in galactic ecosystems, preventing unchecked growth and promoting long-term stability. While it's challenging to ascribe purpose to cosmic phenomena, black holes contribute to the universe's overall dynamism and complexity. They act as engines of change, redistributing matter and energy across vast scales, and potentially even connecting different regions of space-time through theoretical constructs like wormholes. In this way, black holes ensure that the cosmic cycle of creation, destruction, and renewal continues, shaping the universe we observe today. The concept of a cyclic universe offers an intriguing perspective on cosmic purpose. In this model, the universe undergoes endless cycles of expansion and contraction, with each cycle potentially lasting trillions of years. This idea suggests that our current universe might be just one iteration in an infinite series of universes. From this viewpoint, cosmic purpose could be seen as the perpetuation of existence itself. Rather than having a single, defined goal, the universe might simply exist to create the conditions for its own rebirth. Each cycle could produce new arrangements of matter and energy, potentially giving rise to different forms of life and consciousness. This cyclical nature also raises questions about the accumulation of information or complexity across cycles. Some theories propose that each new universe might retain some imprint from its predecessor, gradually evolving and becoming more intricate over time. In this sense, the cosmic purpose could be a form of universal learning or growth on an unimaginable timescale. However, it is important to note that the cyclic universe model remains a theoretical concept. While it offers fascinating possibilities for contemplating cosmic purpose, our current understanding of the universe's ultimate fate and any potential cycles remains limited. The search for evidence supporting or refuting this model continues to drive exciting research in cosmology and theoretical physics. Matter-antimatter cycles played a crucial role in shaping the early universe we observe today. In the first fractions of a second after the Big Bang, the universe was an incredibly hot and dense soup of particles and energy. During this period, matter and antimatter particles were constantly being created and annihilated in a cosmic dance of creation and destruction. These cycles were essential for establishing the conditions necessary for the formation of stable matter. As the universe expanded and cooled, a slight imbalance emerged between matter and antimatter. This asymmetry, known as baryogenesis, is one of the most profound mysteries in cosmology. For every billion antimatter particles, there were 1,000,000,001 matter particles. The majority of matter and antimatter annihilated each other, releasing enormous amounts of energy in the process. This energy contributed to the cosmic microwave background radiation we observe today. The surviving matter, that tiny fraction that remained after the annihilation, went on to form the stars, galaxies, and ultimately, everything we see in the universe. Understanding these early matter-antimatter cycles is crucial for unraveling the origins of our universe. Scientists continue to investigate this phenomenon, seeking to explain why matter ultimately prevailed and how this fundamental asymmetry arose in the first place. This quest not only sheds light on our cosmic history, but also has implications for our understanding of particle physics and the nature of reality itself. Theories of cosmic rebirth, such as eternal inflation, offer intriguing perspectives on the nature and potential purpose of our universe. Eternal inflation proposes that our universe is just one of countless bubble universes continually forming within an ever-expanding cosmic framework. This concept challenges traditional notions of a singular universe with a definite beginning and end. In the context of universal purpose, eternal inflation suggests a cycle of creation and destruction on a scale far beyond our observable universe. Each bubble universe might have its own physical laws, constants, and potential for life. This vast multiplicity of universes could be seen as a cosmic laboratory, testing out different combinations of fundamental parameters. Some scientists and philosophers argue that this continuous creation of universes might serve a greater purpose, such as maximizing the diversity of physical realities or increasing the likelihood of producing universes capable of supporting conscious life. However, it is important to note that ascribing purpose to these cosmic processes remains a philosophical interpretation rather than a scientific conclusion. Ultimately, theories like eternal inflation expand our understanding of the cosmos and our place within it, prompting us to reconsider what we mean by universal purpose in a potentially infinite and ever-changing multiverse. Supernovae are cosmic powerhouses that play a crucial role in enriching the universe with heavy elements. These stellar explosions occur when massive stars reach the end of their lives or when white dwarfs in binary systems accumulate too much material. During these cataclysmic events, intense heat and pressure forge elements heavier than iron, such as gold, silver, and uranium. As the explosive debris disperses into space, it seeds the surrounding cosmic environment with these newly created elements. This process of chemical enrichment is fundamental to the evolution of galaxies and the formation of new stars and planets. The heavy elements produced by supernovae become part of the raw material from which future generations of stars and their planetary systems are born. Moreover, supernovae contribute to the cycle of stellar birth and death by triggering the collapse of nearby gas clouds. The shock waves from these explosions can compress interstellar material, initiating the formation of new stars. This cosmic recycling process ensures a continuous supply of diverse elements throughout the universe. In terms of potential purpose, supernovae serve as cosmic factories that create the building blocks necessary for complex chemistry and, ultimately, life as we know it. Without these stellar explosions, the universe would be composed primarily of hydrogen and helium, lacking the rich diversity of elements that make up our world and enable the existence of life. Cosmic inflation provides a fascinating link to the idea of cyclical universe creation. This theory suggests that in the earliest moments after the Big Bang, our universe underwent a period of exponential expansion. During this brief but intense phase, space itself grew at an incredible rate, far faster than the speed of light. Some cosmologists propose that this inflationary period might not be unique to our universe. Instead, they suggest it could be part of a grander, cyclical process. In this view, universes could spawn new universes through localized regions of inflation. Each new inflating region would become its own universe, separate from its parent, with its own laws of physics and fundamental constants. This concept ties into the idea of a multiverse, where our universe is just one of many. Each universe in this scenario would go through its own cycle of birth, expansion, and potentially spawn new universes. This process could theoretically continue indefinitely, creating a vast cosmic landscape of universes budding from one another. While these ideas are highly speculative and currently beyond our ability to test observationally, they highlight how the concept of inflation opens up new possibilities for understanding the origin and potential multiplicity of universes. The notion of cyclic creation through inflation offers a compelling framework for contemplating the broader context of our cosmic existence. Galaxy mergers offer a fascinating window into the dynamic processes that shape our universe. These colossal events, where two or more galaxies collide and combine, reveal the constant cycle of destruction and creation that occurs on a cosmic scale. As galaxies merge, their gas and dust clouds are compressed, triggering bursts of star formation that illuminate the cosmos with brilliant new light. The study of these mergers provides crucial insights into how galaxies evolve over time. By observing different stages of galactic collisions, scientists can piece together the life cycles of these immense stellar cities. This knowledge helps us understand our own Milky Way's past and future, as it too will eventually merge with the neighboring Andromeda galaxy. Moreover, galaxy mergers demonstrate the interconnectedness of cosmic structures. The gravitational dance of merging galaxies shows how the largest objects in the universe influence each other, shaping the cosmic web of matter that spans billions of light years. This interconnectedness suggests a universe that is far from static, but rather in a constant state of change and renewal. While the concept of cosmic purpose remains a philosophical question, the study of galaxy mergers reveals a universe that continually reinvents itself. Through these epic collisions, the elements forged in ancient stars are recycled into new cosmic structures, perpetuating the cycle of stellar life and death that ultimately led to our own existence. Dark matter plays a crucial role in shaping the structure of the universe, despite its mysterious nature. This invisible form of matter, which does not interact with light or other forms of electromagnetic radiation, exerts a powerful gravitational influence on visible matter. Scientists have detected dark matter's presence through its gravitational effects on galaxies and galaxy clusters. It acts as a cosmic scaffold, forming an extensive network of filaments and nodes known as the cosmic web. This web-like structure guides the distribution of visible matter, influencing the formation and growth of galaxies and galaxy clusters throughout the universe. Dark matter's gravitational pull has been instrumental in the evolution of cosmic structures since the early universe. It provided the initial gravitational seeds that allowed matter to clump together, eventually forming the first stars and galaxies. Without dark matter, the universe would likely be a vastly different place, with fewer large-scale structures and a more uniform distribution of visible matter. Regarding the potential purpose of the universe, dark matter's role remains a subject of scientific inquiry and philosophical debate. While it does not have a predetermined purpose in a teleological sense, dark matter's presence and effects are fundamental to our understanding of cosmic evolution and the universe's current state. Its study continues to push the boundaries of our knowledge, challenging our perceptions of the cosmos and driving advancements in physics and cosmology. Dark energy is a mysterious force that permeates all of space, pushing the universe apart. It plays a crucial role in the accelerating expansion of the cosmos, counteracting the pull of gravity on large scales. Unlike ordinary matter and energy, dark energy exerts a repulsive force, causing galaxies and galaxy clusters to move away from each other at an ever-increasing rate. The discovery of dark energy in the late 1990s revolutionized our understanding of the universe's fate. Before this revelation, scientists believed that the expansion of the universe would eventually slow down due to gravity. However, observations of distant supernovae showed that the expansion is actually speeding up, leading to the conclusion that dark energy must exist. This accelerating expansion, driven by dark energy, has profound implications for the ultimate fate of our universe. If dark energy continues to dominate, the cosmos will expand forever, growing increasingly cold and sparse. This scenario, known as the Big Freeze, suggests that over immense timescales, galaxies will become so distant from each other that they will be effectively isolated, unable to see or interact with one another. The nature of dark energy remains one of the biggest mysteries in modern cosmology. Scientists are working to understand its properties and origins, as this knowledge could provide crucial insights into the fundamental workings of our universe and its long-term evolution. The role of dark energy in shaping the cosmos highlights how much we still have to learn about the vast, enigmatic realm we inhabit. Dark matter plays a crucial role in shaping the structure of our universe, acting as an invisible scaffolding that guides the formation of galaxies. This mysterious substance, which does not interact with light or other forms of electromagnetic radiation, exerts a powerful gravitational influence on visible matter. During the early stages of the universe, dark matter began to clump together, forming dense regions that attracted normal matter. These dark matter concentrations served as cosmic seeds, drawing in gas and dust to form the first stars and galaxies. As time progressed, these initial structures merged and grew, creating the vast cosmic web we observe today. The distribution of dark matter continues to influence galaxy formation and evolution. It forms halos around galaxies, extending far beyond the visible boundaries of stars and gas. These halos not only provide additional gravitational binding, keeping galaxies intact, but also affect their rotation and shape. The interplay between dark matter and visible matter determines the characteristics of different galaxy types, from spirals to ellipticals. While the concept of cosmic purpose is more philosophical than scientific, the ubiquitous presence of dark matter and its fundamental role in cosmic structure raises intriguing questions about the nature of our universe. The fact that dark matter appears to be essential for the formation of galaxies, and by extension, the emergence of life as we know it, adds a layer of complexity to our understanding of the cosmos and our place within it. The cosmic web stands as a monumental structure in our universe, intricately linked to the distribution of dark matter. This vast network of filaments and voids stretches across the cosmos, forming a scaffold upon which galaxies and galaxy clusters are arranged. Dark matter, though invisible to our telescopes, plays a crucial role in shaping this cosmic architecture. Gravitational simulations and observations reveal that dark matter forms the backbone of the cosmic web. Its immense gravitational influence draws ordinary matter along these dark matter filaments, creating rivers of galaxies that flow towards dense nodes where multiple filaments intersect. These intersections become the birthplaces of massive galaxy clusters, the largest gravitationally bound structures in the universe. The relationship between the cosmic web and dark matter distribution provides vital clues about the early universe and the processes of cosmic structure formation. By studying the patterns and properties of the cosmic web, scientists can infer the characteristics and behavior of dark matter, helping to constrain theoretical models and advance our understanding of this enigmatic substance. Furthermore, the cosmic web serves as a cosmic laboratory for testing theories of gravity and the nature of dark energy. As we map the web with increasing precision, we gain insights into the fundamental forces and components that shape our universe on the grandest scales. Dark flow is a controversial concept in cosmology that challenges our understanding of the universe's large-scale structure and motion. This phenomenon suggests that galaxy clusters across vast regions of space are moving in a unified direction, as if being pulled by an unseen force beyond the observable universe. The idea of dark flow emerged from observations of the cosmic microwave background radiation, the afterglow of the Big Bang. Scientists noticed that some galaxy clusters appeared to be moving faster than expected in a particular direction. This coherent motion, if confirmed, could indicate the presence of massive structures or regions of higher density outside our cosmic horizon, exerting a gravitational pull on the matter we can observe. Dark flow relates to our understanding of cosmic structure by potentially revealing the influence of parts of the universe we cannot directly see. It raises questions about the uniformity and isotropy of space on the largest scales, principles that form the foundation of our current cosmological models. If dark flow is real, it might suggest that the universe is more interconnected and complex than we previously thought. However, the existence of dark flow remains debated in the scientific community. Some studies have failed to detect this phenomenon, while others continue to find evidence supporting it. As we develop more advanced observation techniques and instruments, we may gain a clearer picture of whether dark flow truly exists and how it fits into our broader understanding of cosmic structure and evolution. Dark matter, though invisible and mysterious, plays a crucial role in shaping the universe as we know it. In the context of habitable environments, its influence is both profound and far-reaching. The gravitational effects of dark matter are essential in the formation of galaxies and large-scale structures in the cosmos. These structures, in turn, provide the necessary conditions for star formation and planetary systems to develop. The presence of dark matter halos around galaxies helps to maintain their structural integrity and influences their rotation. This stability is vital for the long-term existence of star systems within these galaxies, providing the time needed for planets to form and life to potentially emerge. Without dark matter, galaxies might not have formed as we see them today, dramatically altering the landscape of potential habitable worlds. Furthermore, dark matter's gravitational pull affects the distribution of normal matter throughout the universe. This distribution determines where stars and planets can form, indirectly influencing the locations where habitable environments might arise. The interplay between dark matter and normal matter creates a cosmic web of filaments and voids, guiding the formation of galaxy clusters and superclusters where life-supporting planets could potentially exist. While dark matter does not interact directly with the elements necessary for life as we know it, its overarching influence on cosmic structure and evolution makes it an essential factor in creating the conditions where habitable environments can emerge. As we continue to study dark matter, we may uncover even more ways in which this elusive substance shapes the potential for life in the universe. The accelerating expansion of the universe, driven by the mysterious force we call dark energy, presents a profound challenge to our understanding of cosmic purpose. This phenomenon, discovered in the late 1990s, reveals that the universe is not only expanding, but doing so at an ever-increasing rate. As galaxies move farther apart more quickly, the universe becomes increasingly sparse and cold. This progression towards a state of maximum entropy, often referred to as the heat death of the universe, seems to suggest a universe that will eventually become incapable of supporting complex structures or life as we know it. However, the concept of purpose in the cosmos is more a philosophical question than a scientific one. While dark energy appears to be hastening the universe towards a state of eternal darkness, it has also played a crucial role in the formation of large-scale structures we see today. Without the delicate balance between the attractive force of gravity and the repulsive force of dark energy, galaxies and galaxy clusters might never have formed. The accelerating expansion also highlights the vast timescales involved in cosmic evolution, prompting us to reconsider our place in the universe's history. Are we merely a fleeting moment in cosmic time, or could life and intelligence be a fundamental aspect of the universe's nature? These questions continue to drive scientific inquiry and philosophical debate, reminding us that our search for cosmic purpose is intimately tied to our understanding of the universe's fundamental forces and its ultimate fate. Gravitational lensing serves as a powerful tool in our quest to understand dark matter and cosmic structure. This phenomenon occurs when massive objects, like galaxy clusters, bend light from distant sources, creating distorted or multiple images. By studying these distortions, astronomers can map the distribution of matter, including the elusive dark matter that doesn't interact with light. One of the most significant insights from gravitational lensing is the confirmation of dark matter's existence. The lensing effects we observe are often much stronger than what visible matter alone could produce. This discrepancy provides compelling evidence for large amounts of invisible mass shaping the cosmos. Furthermore, gravitational lensing allows us to probe the structure of the universe on vast scales. By analyzing the patterns of lensed images across the sky, scientists can trace the cosmic web of dark matter filaments that connect galaxies and clusters. This technique reveals how matter clumps together over time, offering crucial insights into the evolution of cosmic structure. Importantly, gravitational lensing also helps us test theories of modified gravity, which attempt to explain cosmic phenomena without invoking dark matter. By comparing observed lensing effects with predictions from different models, researchers can evaluate alternative explanations for the universe's behavior, furthering our understanding of fundamental physics and cosmology. Dark energy, the mysterious force causing the accelerated expansion of the universe, plays a crucial role in shaping its long-term fate. As dark energy continues to push galaxies apart at an ever-increasing rate, it fundamentally alters the cosmic landscape and our understanding of the universe's ultimate destiny. The strength and nature of dark energy will determine whether the universe expands forever or eventually reverses course. If dark energy remains constant or increases over time, the universe will likely experience a big freeze scenario. In this future, galaxies will become increasingly isolated, stars will burn out, and the cosmos will grow colder and darker. Eventually, even atoms might be torn apart in an event known as the Big Rip. However, if dark energy weakens or changes its behavior, other outcomes become possible. A decreasing dark energy could lead to a big crunch where gravity overcomes expansion, causing the universe to collapse back in on itself. Alternatively, a cycling universe might emerge, expanding and contracting in an endless cosmic dance. The properties of dark energy also influence structure formation in the universe. Its repulsive force counteracts gravity, potentially slowing or halting the growth of cosmic structures like galaxy clusters. This interplay between dark energy and gravity shapes the large-scale structure of the cosmos and affects the distribution of matter throughout space. Dark matter halos are crucial to our understanding of galaxy evolution and structure in the universe. These invisible, massive structures surround galaxies and galaxy clusters, exerting a powerful gravitational influence on visible matter. As galaxies form and evolve, dark matter halos act as cosmic scaffolding, providing the gravitational wells that allow gas and stars to coalesce and form the luminous structures we observe. The relationship between dark matter halos and galaxies is complex and symbiotic. As galaxies grow, they do so within the confines of their dark matter halos, which in turn grow through mergers with other halos and by accreting material from their surroundings. This process shapes the distribution of galaxies we see in the cosmic web, with larger halos hosting more massive galaxies and smaller halos containing dwarf galaxies or remaining dark. Dark matter halos also play a role in regulating star formation within galaxies. Their gravitational effects influence gas dynamics, potentially triggering or suppressing star formation depending on the circumstances. This interplay between dark and visible matter helps explain the diverse range of galaxy types and sizes we observe in the universe. While the concept of cosmic purpose is more philosophical than scientific, dark matter halos are undeniably fundamental to the large-scale structure of the universe. They provide the gravitational framework that has allowed complexity to emerge in the cosmos, from the formation of galaxies to the birth of stars and planets. In this sense, dark matter halos could be seen as essential facilitators in the grand cosmic story, enabling the universe to develop the rich, varied structures we see today. Quantum mechanics, the study of nature at its smallest scales, has profound implications for our understanding of the universe and our place within it. This branch of physics reveals a world of probabilities and uncertainties, challenging our classical notions of cause and effect. At the quantum level, particles can exist in multiple states simultaneously, only settling into a definite state when observed. This phenomenon, known as superposition, suggests that reality is not fixed until it is measured. The implications of quantum mechanics extend far beyond the subatomic realm. Some scientists propose that the entire universe might operate on quantum principles, with multiple possible futures coexisting until they collapse into a single reality. This idea, while speculative, raises intriguing questions about free will and the nature of consciousness. Furthermore, quantum entanglement, where particles can instantaneously influence each other regardless of distance, hints at a deeply interconnected universe. This concept challenges our understanding of space and time, suggesting that separateness might be an illusion. Some philosophers and scientists argue that this interconnectedness could be a fundamental aspect of cosmic purpose. While quantum mechanics does not directly address questions of cosmic purpose, it does reshape our understanding of reality in ways that may inform our search for meaning. By revealing a universe more strange and wondrous than we ever imagined, quantum physics invites us to reconsider our place within the cosmic tapestry and the nature of existence itself. Quantum entanglement plays a fascinating and profound role in shaping the structure of our universe. This peculiar quantum phenomenon, where particles become intrinsically linked regardless of the distance between them, has far-reaching implications for the fabric of space and time. At the smallest scales, quantum entanglement influences how particles interact and behave. These interactions form the foundation for larger structures in the cosmos. For instance, entanglement affects the way atoms bond to form molecules, which in turn impacts the formation of stars, planets, and even complex organic compounds. On a grander scale, quantum entanglement may be key to understanding the nature of black holes and the information they contain. Some theories suggest that entanglement between particles inside and outside a black hole's event horizon could resolve the infamous black hole information paradox, potentially preserving information that was thought to be lost. Perhaps most intriguingly, quantum entanglement might be the thread that weaves the fabric of space-time itself. According to some models, the intricate network of entangled particles could give rise to the emergent properties of space and time as we experience them, fundamentally shaping the structure and behavior of our entire universe. The many worlds interpretation of quantum mechanics proposes that every possible outcome of a quantum event occurs, each in its own separate universe. This mind-bending concept suggests our universe is just one of countless parallel realities, constantly branching off with each quantum interaction. When we consider cosmic purpose in light of this interpretation, it raises profound questions about the nature of existence and meaning. If every possible outcome occurs somewhere in the multiverse, does that negate the idea of a single, overarching purpose for our particular universe? Or does it instead expand our understanding of purpose to encompass all possible realities? Some theorists argue that the many worlds interpretation actually strengthens the case for cosmic purpose. They suggest that the existence of infinite parallel universes allows for the exploration of all potential paths and outcomes, ultimately fulfilling a greater cosmic goal of realizing every possibility. In this view, our universe and all its counterparts serve a collective purpose of manifesting all conceivable realities. Critics, however, contend that the sheer vastness of possibilities in a many-worlds scenario dilutes the concept of purpose. They argue that if every outcome occurs, then no particular outcome can be considered special or purposeful. This perspective challenges us to reconsider what we mean by purpose on a cosmic scale and whether it remains a relevant concept in a potentially infinite multiverse. Quantum tunneling plays a crucial role in the evolution of the universe, influencing processes from the smallest subatomic scales to the vast expanses of cosmic structures. This phenomenon, rooted in quantum mechanics, allows particles to pass through energy barriers that classical physics would deem impossible. In the early universe, quantum tunneling was instrumental in the process of cosmic inflation. This rapid expansion period, occurring just fractions of a second after the Big Bang, was likely triggered by a quantum tunneling event. The universe transitioned from a false vacuum state to a lower energy state, releasing enormous amounts of energy and expanding space at an incredible rate. On stellar scales, quantum tunneling enables nuclear fusion in stars. It allows protons to overcome their electrostatic repulsion and fuse, releasing energy that powers stars for billions of years. Without this quantum effect, stars like our Sun would not shine, and the heavier elements essential for life would not be created. Quantum tunneling also plays a role in more exotic cosmic phenomena. It contributes to Hawking radiation from black holes, where particles can tunnel out of the event horizon, causing black holes to slowly evaporate over time. This process connects quantum mechanics with gravity, providing insights into the fundamental nature of our universe and its long-term evolution. The uncertainty principle, a fundamental concept in quantum mechanics, has profound implications for our understanding of the universe, including our quest to determine cosmic purpose. This principle, formulated by Werner Heisenberg, states that we cannot simultaneously measure certain pairs of physical properties with perfect accuracy. For instance, the more precisely we measure a particle's position, the less precisely we can know its momentum, and vice versa. When we extend this principle to the cosmic scale, it introduces a level of inherent unpredictability into the fabric of the universe. This unpredictability challenges the notion of a predetermined cosmic purpose or destiny. If we cannot precisely know both the position and momentum of particles at the quantum level, it becomes difficult to assert with certainty that the universe follows a predetermined path or has a specific, predefined purpose. Furthermore, the uncertainty principle suggests that the act of observation itself can influence the outcome of an experiment. This raises questions about our role as observers in the universe and how our very presence might affect the cosmic narrative. It challenges the idea of an objective, unchanging reality and implies that our search for cosmic purpose might be intrinsically linked to our participation in the universe. The uncertainty principle also highlights the limits of human knowledge and our ability to fully comprehend the universe. As we strive to understand cosmic purpose, we must acknowledge that there may always be aspects of reality that remain beyond our grasp. This inherent uncertainty does not necessarily negate the existence of cosmic purpose, but it does suggest that our understanding of it may always be incomplete or subject to change as we continue to explore and observe the universe around us. Quantum coherence, a phenomenon typically associated with the microscopic realm of atoms and particles, has been found to play surprising roles in biological systems. Recent research has uncovered evidence of quantum effects in processes like photosynthesis and bird navigation, challenging our understanding of the boundary between quantum and classical worlds. In photosynthesis, for example, light-harvesting complexes in plants and some bacteria appear to use quantum coherence to efficiently transfer energy from absorbed light to reaction centers. This quantum-assisted process allows these organisms to capture and use solar energy with remarkable efficiency, potentially giving them an evolutionary advantage. The potential implications of quantum coherence in biology extend beyond individual organisms to broader questions about life and its place in the cosmos. Some researchers speculate that quantum effects might be fundamental to the emergence and persistence of life itself, suggesting a deeper connection between the quantum world and biological complexity. As for cosmic purpose, the presence of quantum coherence in biological systems has led some to propose that life might play a role in the universe's evolution toward greater complexity and information processing capability. While highly speculative, these ideas raise intriguing questions about the nature of life, consciousness, and the fundamental fabric of reality. Quantum field theory offers profound insights into the fundamental nature of reality, pushing our understanding of the universe's structure to new frontiers. This powerful framework combines quantum mechanics with special relativity, providing a description of subatomic particles as excitations in underlying fields that permeate all of space. By viewing particles as field fluctuations rather than discrete objects, quantum field theory helps explain phenomena like particle creation and annihilation. This perspective is crucial for comprehending the behavior of matter and energy at the smallest scales, which in turn shapes the larger structures we observe in the cosmos. One of the most significant contributions of quantum field theory is its role in the Standard Model of particle physics. This model describes the interactions between fundamental particles and forces, except gravity, with remarkable precision. Understanding these interactions is key to unraveling the processes that occurred in the early universe and continue to influence its evolution today. Quantum field theory also provides a framework for exploring the vacuum state of space itself. Far from being empty, the quantum vacuum is teeming with virtual particles that constantly pop in and out of existence. This concept has far-reaching implications, potentially explaining phenomena like dark energy, which drives the accelerating expansion of the universe. Virtual particles play a crucial role in our understanding of cosmic evolution, influencing fundamental processes at both the quantum and cosmic scales. These fleeting entities emerge spontaneously from the quantum vacuum, existing for incredibly brief moments before disappearing again. Their significance lies in their ability to mediate forces between particles and contribute to the energy of empty space. In the early universe, virtual particles had a profound impact on the rapid expansion during the inflationary period. The energy fluctuations caused by these particles are believed to have seeded the initial density variations that eventually led to the formation of large-scale structures we observe today, such as galaxies and galaxy clusters. Virtual particles also play a key role in black hole physics. Stephen Hawking proposed that virtual particle pairs created near a black hole's event horizon could lead to black hole evaporation. One particle of the pair might fall into the black hole, while the other escapes, resulting in a gradual loss of mass for the black hole over time. This process, known as Hawking radiation, has significant implications for the long-term evolution of black holes and the universe as a whole. Furthermore, virtual particles contribute to the vacuum energy of space, which is closely related to the cosmological constant in Einstein's equations of general relativity. This vacuum energy is thought to be a driving force behind the observed accelerating expansion of the universe, shaping its large-scale structure and ultimate fate. Quantum foam is a fascinating concept that delves into the very nature of space-time at its smallest scales. At incredibly tiny distances, far smaller than even subatomic particles, space-time is thought to be in constant flux, bubbling and roiling with energy. This turbulent sea of virtual particles popping in and out of existence gives rise to a foam-like structure, hence the term quantum foam. This concept directly challenges our conventional understanding of space-time as a smooth, continuous fabric. Instead, at the quantum scale, space-time becomes a seething cauldron of activity, where the laws of physics as we know them begin to break down. The quantum foam represents the fundamental limit of our ability to measure and understand the universe, as it exists at scales so small that our current theories and instruments cannot probe them directly. The potential purpose of quantum foam is multifaceted. It may serve as the underlying structure from which all matter and energy in the universe emerges. Some theories suggest that these quantum fluctuations could be the source of the mysterious dark energy that is causing the accelerated expansion of the universe. Additionally, quantum foam might play a crucial role in reconciling quantum mechanics with general relativity, potentially leading to a unified theory of quantum gravity. Understanding quantum foam could also have profound implications for our comprehension of the nature of reality itself. It challenges our notions of emptiness and fullness, suggesting that even the seemingly empty vacuum of space is teeming with activity at the quantum level. This concept pushes the boundaries of our understanding, inviting us to reconsider the fundamental nature of space, time, and the universe itself. Quantum gravity stands at the forefront of modern physics, promising to bridge the gap between quantum mechanics and general relativity. This elusive theory could provide a unified description of all fundamental forces in the universe, from the tiniest subatomic particles to the largest cosmic structures. At the quantum scale, the effects of gravity are typically negligible. However, in extreme conditions such as the early universe or inside black holes, both quantum mechanics and gravity become equally important. A theory of quantum gravity would allow us to understand these extreme environments, potentially revealing new insights about the nature of space and time. One of the most intriguing implications of quantum gravity is its potential to explain the origin of the universe. It might provide a framework to describe the universe before the Big Bang, addressing questions about the initial singularity and the very fabric of space-time. This could revolutionize our understanding of cosmic evolution and the fundamental nature of reality. Moreover, quantum gravity could help resolve long-standing puzzles in cosmology, such as the nature of dark energy and dark matter. By offering a more complete picture of how gravity behaves at all scales, it might unveil hidden connections between the quantum world and the large-scale structure of the universe, leading to a more comprehensive and elegant description of the cosmos. The various models predicting the ultimate fate of our universe offer intriguing insights into its potential purpose, if indeed such a purpose exists. The expanding universe we observe today could lead to several possible outcomes, each with profound implications for the nature of existence. One model suggests a continually expanding universe, eventually leading to a cold, dark expanse where all matter and energy are spread so thin that no further interactions occur. This scenario, often called the Big Freeze, might imply a universe without a defined endpoint or goal, simply expanding until it reaches a state of maximum entropy. Another possibility is the Big Crunch, where the expansion of the universe eventually reverses, leading to a cosmic contraction. All matter and energy would ultimately collapse back into a singularity, potentially setting the stage for a new Big Bang. This cyclic model could suggest a universe that continually renews itself, perhaps allowing for multiple iterations of existence and the potential for different physical laws in each cycle. The Big Rip theory proposes that the expansion of the universe will accelerate to such an extent that it tears apart all structures, from galaxies down to subatomic particles. This outcome might indicate a universe with an inherent drive towards dissolution, challenging our notions of permanence and stability. These different models prompt us to consider whether the universe has a specific direction or purpose, or if it simply exists and evolves according to fundamental physical laws. The fate of the universe, whatever it may be, invites us to contemplate our place within this vast cosmic story and the meaning we ascribe to our existence within it. The Big Freeze scenario presents a stark perspective on the ultimate fate of our universe, challenging our notions of cosmic purpose. This theory suggests that as the universe continues to expand, it will gradually cool down, leading to a state of maximum entropy where all matter and energy are evenly distributed. In this scenario, stars would eventually exhaust their fuel and die out, leaving behind a cold, dark cosmos devoid of life and activity. Galaxies would drift apart, and even subatomic particles would decay, resulting in a universe filled with nothing but an extremely diffuse soup of fundamental particles and radiation. The Big Freeze raises profound questions about the long-term meaning and purpose of existence. If the universe is destined to end in a state of eternal darkness and inactivity, it might seem to negate any grand cosmic plan or purpose. This can be unsettling for those who seek meaning in the larger context of the universe. However, the Big Freeze scenario also highlights the preciousness of our current cosmic era. It underscores the unique window of time in which complex structures, life, and consciousness can exist. This perspective can inspire us to appreciate and make the most of our brief moment in cosmic history, potentially giving rise to a different kind of purpose focused on the present rather than an eternal future. The Big Crunch theory proposes a potential end to our universe where gravity overcomes the force of expansion, causing all matter to collapse back into an incredibly dense state. This idea naturally connects to the concept of cosmic cycles, suggesting that our universe might be part of a grand, repeating pattern of expansion and contraction. In this cyclical view, each Big Crunch could lead to a new Big Bang, birthing an entirely new universe. This endless cycle of death and rebirth on a cosmic scale echoes patterns we observe in nature, from the changing seasons to the life cycles of stars. It offers a compelling alternative to the idea of a universe with a definitive beginning and end. The notion of cosmic cycles raises intriguing questions about purpose and meaning in the universe. If the cosmos follows a cyclical pattern, it might suggest a deeper order or structure to reality beyond our current understanding. Some find this idea comforting, as it implies a form of cosmic continuity and perhaps even purpose. However, it is important to note that current observations suggest our universe is expanding at an accelerating rate, making the Big Crunch scenario less likely. Nevertheless, the concept continues to fascinate scientists and philosophers alike, inspiring us to ponder the ultimate fate and potential rebirth of our cosmos. Heat death is a central concept in discussions about the ultimate fate of the universe. This idea stems from the second law of thermodynamics, which states that entropy or disorder always increases in a closed system over time. In the context of the universe, heat death represents the final state where all energy is evenly distributed and no work can be done. As the universe continues to expand and cool, stars will eventually exhaust their fuel and die out. Galaxies will disperse, and black holes will evaporate through Hawking radiation. Over unimaginably long timescales, all matter and energy will spread out uniformly across the vastness of space. This results in a state of maximum entropy, where no temperature differences exist to drive physical processes or sustain life. The concept of heat death challenges our understanding of time and existence. It suggests that the universe might reach a state of equilibrium where nothing meaningful can occur. This idea has profound implications for the long-term future of life and consciousness in the cosmos. Some scientists speculate about potential ways to avoid or delay this fate, such as the creation of new universes or the exploitation of dark energy. Heat death serves as a sobering reminder of the finite nature of our universe and prompts discussions about the meaning and purpose of existence in the face of cosmic timescales. It underscores the importance of understanding fundamental physics and cosmology as we contemplate the ultimate destiny of everything we know. The Big Rip scenario presents a profound challenge to our understanding of cosmic purpose. This hypothetical end of the universe suggests that the mysterious force known as dark energy could become so powerful that it tears apart everything in existence, from galaxies and stars down to atoms themselves. As we contemplate this potential fate, we are forced to confront the impermanence of not just life, but of all physical structures in the cosmos. The Big Rip implies that even the most fundamental building blocks of matter would ultimately be destroyed, leaving behind an empty, featureless void. This concept pushes us to question whether the universe has an overarching purpose or if it is simply following the inevitable consequences of its initial conditions and physical laws. However, the Big Rip scenario also highlights the incredible complexity and dynamism of our universe. It demonstrates that the cosmos is not static, but constantly evolving and changing on scales far beyond human experience. This realization can inspire a sense of awe and wonder at the sheer magnitude of cosmic processes. Moreover, the possibility of the Big Rip encourages us to value the present moment and the current state of the universe. If all structures are destined to be torn apart, then the complex forms we see today, from planets to living organisms, become even more precious and remarkable. This perspective might lead us to find purpose in the journey of cosmic evolution rather than in any final state or endpoint. Vacuum decay is a concept that challenges our understanding of the universe's stability. It suggests that our universe might not be in its most stable state, but rather in a temporary, false vacuum. This false vacuum could potentially transition to a true vacuum state, an event that would have profound consequences for the fabric of reality as we know it. The idea stems from quantum field theory, which describes the universe as a collection of fields. These fields have different energy levels, and our current universe exists at a specific energy level. However, there may be lower energy states that are more stable. If a small region of space were to drop to this lower energy state, it could create a bubble of true vacuum that would expand at nearly the speed of light, engulfing everything in its path. This process would fundamentally alter the laws of physics within the bubble. Atoms as we know them might cease to exist, and the basic forces that hold matter together could change or disappear entirely. The expansion of this bubble would be unstoppable, eventually encompassing the entire observable universe. The significance of vacuum decay lies in its potential to completely reshape or even destroy our universe. However, it is important to note that if such an event were to occur, it would happen instantaneously from our perspective, leaving no time for observation or reaction. While the concept of vacuum decay is based on established physics, whether it could actually occur remains a topic of ongoing research and debate among cosmologists and particle physicists. The steady-state theory proposed a universe that remains essentially unchanged over time, with matter continuously created to maintain a constant average density. This concept contrasts sharply with the now widely accepted Big Bang theory, which describes a universe with a definite beginning and ongoing expansion. In terms of cosmic purpose, the steady-state model presented a universe without a clear starting point or ultimate end. This eternal, unchanging cosmos might suggest a lack of overall direction or goal. Some viewed this as a universe devoid of inherent meaning, while others saw it as a realm of endless possibilities and continuous renewal. However, the discovery of the cosmic microwave background radiation and other evidence supporting the Big Bang theory has largely discredited the steady-state model. The current understanding of an expanding universe with a definite beginning raises different questions about cosmic purpose. It invites contemplation on the nature of time, the potential for a cosmic life cycle, and the role of complexity and life within an evolving universe. Ultimately, the relationship between cosmological models and notions of cosmic purpose remains a subject of philosophical and scientific debate, touching on fundamental questions about existence, meaning, and our place in the universe. The expansion rate of the universe is a crucial factor in determining its ultimate fate. This rate, known as the Hubble constant, measures how quickly galaxies are moving away from each other as the universe expands. The interplay between this expansion and the gravitational pull of all the matter in the universe shapes the cosmic future. If the expansion rate is relatively slow, gravity might eventually overcome it, causing the universe to stop expanding and start contracting. This scenario, called the Big Crunch, would end with all matter and energy condensed into an incredibly hot, dense state similar to the beginning of the universe. Conversely, if the expansion rate is fast enough to overcome gravity, the universe will continue to expand forever. This could lead to a big freeze, where the universe becomes increasingly cold and sparse as stars burn out and matter spreads thin across vast distances. Another possibility is the Big Rip, where expansion accelerates to such an extreme that it tears apart all structures, from galaxies down to atoms. Current observations suggest that the expansion of the universe is actually accelerating, driven by a mysterious force called dark energy. This acceleration points towards an ever-expanding universe, but the nature of dark energy remains one of the biggest mysteries in cosmology, leaving the ultimate fate of the universe an open question. Cosmic phase transitions are pivotal moments in the evolution of our universe, marking distinct shifts in its fundamental properties. These transitions are akin to how water changes from ice to liquid to vapor, but on a cosmic scale. As the universe expanded and cooled following the Big Bang, it underwent several phase transitions that shaped its current state and will continue to influence its future. One of the most significant phase transitions occurred just moments after the Big Bang, when the universe cooled enough for quarks to combine into protons and neutrons. This transition set the stage for the formation of atoms and eventually the complex structures we see today. Looking forward, physicists speculate about potential future phase transitions that could dramatically alter the universe's landscape. A particularly intriguing possibility is the idea of vacuum decay. Our current universe might be in a false vacuum state, temporarily stable but not at its lowest energy level. A transition to a true vacuum state could alter fundamental constants and potentially change the laws of physics themselves. This shift could render our universe unrecognizable or even inhospitable to life as we know it. Another potential phase transition involves dark energy, the mysterious force driving the accelerated expansion of the universe. Some theories suggest that dark energy's properties might change over time, leading to a phase transition that could alter the universe's expansion rate. This could result in scenarios ranging from a big rip, where expansion tears apart all structures, to a big crunch, where gravity overcomes expansion and the universe collapses back on itself. White dwarfs and neutron stars offer crucial insights into the ultimate destiny of our universe. These stellar remnants represent the final stages of stellar evolution for most stars, providing a glimpse into the far future of our cosmos. White dwarfs, the remnants of low to medium mass stars, are incredibly dense objects about the size of Earth, but with masses comparable to our Sun. They no longer generate energy through fusion and gradually cool over billions of years. By studying the oldest white dwarfs, astronomers can estimate the age of the universe and project how long these stellar corpses will continue to glow before fading into darkness. Neutron stars, formed from more massive stars, are even denser than white dwarfs. Their study reveals the behavior of matter under extreme conditions and sheds light on the processes that shape the universe. The existence of these ultra-dense objects confirms our understanding of stellar evolution and supports theories about the life cycles of stars and galaxies. Both white dwarfs and neutron stars play a role in our understanding of dark energy, the mysterious force driving the accelerating expansion of the universe. By observing how these objects behave across vast distances, scientists can refine their models of cosmic expansion and better predict the long-term fate of the universe. This research suggests that the universe may continue expanding indefinitely, eventually resulting in a cold, dark cosmos populated by these stellar remnants long after the last stars have burned out. The concept of a simulated universe raises profound questions about cosmic purpose and the nature of reality itself. This idea suggests that our entire universe, including all its inhabitants, might be an incredibly complex computer simulation created by an advanced civilization or intelligence. If our universe is indeed simulated, it could imply that there is a purpose or intent behind its creation. The simulators might have specific goals or experiments in mind, using our universe as a vast laboratory to study emergent behaviors, test theories, or explore different possibilities of existence. This perspective could give new meaning to the idea of cosmic purpose, framing it not as an inherent property of the universe, but as a design feature imposed by external creators. However, the simulated universe hypothesis also challenges traditional notions of purpose. If we are simulated beings, our perceived free will and sense of purpose might be illusory, programmed into us by the simulation's creators. This raises complex philosophical questions about the nature of consciousness, reality, and meaning. Importantly, even if we are living in a simulation, it does not necessarily negate the value or significance of our experiences and discoveries. The laws of physics, the beauty of the cosmos, and the wonder of existence would still be real to us within the context of the simulation. The search for purpose and meaning would remain a fundamental part of the human experience, simulated or not. The simulation hypothesis challenges our fundamental understanding of reality, suggesting that our entire universe might be an advanced computer simulation created by a more technologically advanced civilization. This concept has profound implications for our perception of existence and consciousness. If we are indeed living in a simulated reality, it would mean that the physical laws we observe and study might be nothing more than programmed rules within the simulation. Our scientific discoveries could be revelations of the underlying code rather than fundamental truths of an objective universe. This possibility raises questions about the nature of free will and determinism, as our actions and thoughts could potentially be predetermined by the simulation's parameters. The simulation hypothesis also has implications for our understanding of consciousness and the nature of the self. If our minds are simulated, it would suggest that consciousness could be replicated or transferred, potentially opening up new avenues for exploring immortality or the nature of the soul. It might also imply that our perceived reality is just one of many possible simulations, with countless other realities existing in parallel. Furthermore, this hypothesis forces us to reconsider our place in the cosmos. If we are simulated beings, we might be part of an experiment, entertainment for advanced beings, or even a complex computation solving problems beyond our comprehension. This perspective could dramatically alter our understanding of purpose and meaning in the universe, challenging us to reevaluate our beliefs and values in light of this potentially simulated existence. Nested simulations and multiple universes are intriguing concepts that challenge our understanding of reality and cosmic purpose. The idea of nested simulations suggests that our universe could be a computer simulation running within another, higher-level universe. This concept extends further, proposing that simulations could exist within simulations, creating a potentially infinite hierarchy of realities. This notion relates to the concept of multiple universes, also known as the multiverse theory. While multiple universes propose the existence of separate, distinct realities, nested simulations suggest a hierarchical structure of realities. Both concepts expand our view of what might exist beyond our observable universe. The implications for cosmic purpose are profound. If we exist within a simulation, it raises questions about the intentions of the simulators. Are we part of a grand experiment, a form of entertainment, or perhaps a way for a higher civilization to explore different possibilities? Similarly, the existence of multiple universes could suggest that our universe is one of many potential outcomes, each with its own unique properties and possibly its own form of life. These ideas challenge traditional notions of cosmic purpose, suggesting that our universe might be part of a larger, more complex system. They invite us to consider that the meaning and purpose we seek might extend beyond the boundaries of our own reality, connecting us to a vast, interconnected web of existence that we are only beginning to contemplate. Computational power is a critical factor in the potential feasibility of universe simulation. As our understanding of the cosmos expands and our technological capabilities advance, the question of whether we could simulate an entire universe becomes increasingly relevant. The sheer scale and complexity of the universe present enormous challenges for any simulation attempt. To accurately model even a small portion of the cosmos would require processing power far beyond our current capabilities. Every atom, every interaction, and every fundamental force would need to be accounted for and calculated in real time. Current supercomputers, while impressive, are still woefully inadequate for such a monumental task. However, the rapid pace of technological advancement offers hope. Quantum computing, with its ability to perform complex calculations exponentially faster than classical computers, could potentially provide the necessary computational power for universe simulation in the future. Even with quantum computing, simulating a universe as vast and intricate as our own remains a distant possibility. The amount of data required to represent every particle and force in the cosmos is almost unimaginable. Yet, as our computational power continues to grow, we may eventually reach a point where simulating smaller, simplified universes becomes feasible, offering new insights into cosmic evolution and the fundamental nature of reality. Digital physics proposes that the universe at its most fundamental level operates like a computer, processing information through discrete binary units rather than continuous processes. This concept aligns closely with the idea of a simulated cosmos, suggesting that our reality might be a sophisticated computer simulation. In digital physics, space and time are not smooth and continuous, but quantized, existing in discrete units like pixels on a screen or bits in a computer. This discreteness mirrors the way information is processed in computer simulations, where complex systems are broken down into manageable, computable units. The simulated cosmos hypothesis posits that an advanced civilization could create a universe simulation so detailed that its inhabitants would be unaware of its artificial nature. If our universe operates on principles of digital physics, it could be seen as evidence supporting this hypothesis, as the underlying structure would be compatible with computational processes. However, it is important to note that while these ideas are intriguing, they remain speculative. Scientists continue to debate and investigate the nature of reality, seeking evidence that could confirm or refute these hypotheses about the fundamental structure of our cosmos. The potential to create simulated universes opens up a fascinating realm of ethical questions. As our computing power and understanding of physics advance, we must grapple with the implications of potentially bringing into existence entire simulated realities. One primary concern is the moral status of simulated beings. If we create a universe simulation detailed enough to produce conscious entities, do we have ethical obligations to these digital life forms? Some argue that simulated beings capable of suffering or experiencing well-being deserve moral consideration, similar to how we extend ethical treatment to animals in our world. Another ethical dilemma involves the level of intervention in simulated universes. Should creators interfere with the events unfolding in their simulations, or allow them to progress naturally? This question mirrors age-old philosophical debates about the nature of free will and determinism, now applied to artificial realities we might create. The possibility of simulated universes also raises questions about our own reality. If it becomes possible to create such detailed simulations, we must consider the likelihood that our own universe might be a simulation created by a more advanced civilization. This scenario, known as the simulation hypothesis, challenges our understanding of existence and the nature of reality itself. The detection of a simulation would profoundly alter our understanding of cosmic purpose, challenging our most fundamental beliefs about reality and our place in the universe. Such a discovery would suggest that our entire cosmos, with its vast galaxies, intricate physical laws, and complex life forms, is an artificial construct created by an advanced intelligence. This revelation would raise profound questions about the nature and intentions of the simulators. Are we part of a grand experiment, a form of entertainment, or perhaps a method of preservation for a long-lost civilization? The purpose of our universe might then be tied to the goals of these creators, shifting our perspective from a naturally evolving cosmos to one with predetermined objectives. Furthermore, the discovery of a simulated universe would have significant implications for our understanding of consciousness and free will. It could suggest that our thoughts and actions are programmed, part of a vast computational process rather than the result of genuine agency. This would challenge our notions of purpose on both a cosmic and personal level. Ultimately, detecting a simulation would not necessarily negate the search for meaning or purpose. Instead, it would add new layers of complexity to these philosophical questions, potentially opening up entirely new avenues of inquiry about the nature of reality, consciousness, and the fundamental purpose of existence itself. Consciousness plays a fascinating and complex role in the realm of simulated realities. As we explore the concept of artificial worlds, we must consider how our awareness and perception might function within these constructed environments. In a simulated reality, consciousness could be viewed as the interface between the artificial world and our subjective experience. It allows us to interpret and interact with the simulated environment, much like our consciousness enables us to navigate the physical world we currently inhabit. However, the nature of consciousness within a simulation raises profound questions about the authenticity of our experiences and the very essence of reality itself. One intriguing possibility is that consciousness could be an emergent property of sufficiently complex simulations. This idea suggests that as artificial worlds become more sophisticated, they might give rise to self-aware entities within the simulation. This concept challenges our understanding of what constitutes genuine consciousness and blurs the line between simulated and real experiences. Furthermore, the role of consciousness in simulated realities forces us to confront the possibility that our own reality might be a simulation. If we can create convincing artificial worlds, how can we be certain that our own consciousness is not part of a grand simulation created by an advanced civilization or even our future selves? This thought experiment, known as the simulation hypothesis, highlights the profound impact that consciousness has on our perception of reality, whether simulated or not. Emergent phenomena play a fascinating role in our understanding of simulated universes and cosmic purpose. These phenomena arise from the complex interactions of simpler components, creating behaviors and properties that cannot be predicted from individual parts alone. In the context of simulated universes, emergent phenomena suggest that even with basic rules governing a system, intricate and unexpected patterns can develop. Consider how simple cellular automata, following elementary rules, can produce astonishingly complex patterns. Similarly, a simulated universe with fundamental laws might give rise to emergent structures and behaviors, including the potential for life and consciousness. This concept challenges our notions of determinism and reductionism, hinting at the possibility that cosmic purpose itself could be an emergent property of the universe. The idea of emergent phenomena in simulated universes also raises intriguing questions about our own reality. If our universe is a simulation, the purpose or intent behind its creation might not be explicitly programmed, but could instead emerge from the interplay of its basic constituents. This perspective suggests that meaning and purpose in the cosmos might not be imposed from outside, but could evolve naturally within the system. Ultimately, the concept of emergence in simulated universes encourages us to consider that cosmic purpose may not be a predetermined directive, but a dynamic, evolving aspect of reality itself. It invites us to explore the possibility that complexity, intelligence, and even purpose could be inherent properties of the universe, emerging from fundamental principles in ways we are only beginning to understand. The simulation hypothesis challenges our traditional notions of free will and determinism in profound ways. If our reality is indeed a simulated construct, it raises questions about the nature of our choices and actions. Are they truly our own, or are they predetermined by the parameters of the simulation? In a simulated universe, every decision and event could potentially be the result of pre-programmed algorithms. This aligns closely with the concept of determinism, where all events are the inevitable consequence of prior causes. If our reality is running on a vast computer system, our thoughts and actions might be nothing more than complex computations, leaving little room for genuine free will. However, the simulation hypothesis does not necessarily negate free will entirely. Even in a simulated environment, the complexity of our consciousness and decision-making processes might still allow for a form of free will within the constraints of the simulation. Just as a video game character can make choices within the game world, we might have agency within the parameters of our simulated reality. Furthermore, the simulation hypothesis introduces the possibility of multiple levels of reality. If we are in a simulation, the beings running that simulation might themselves be in a higher-level simulation. This recursive nature complicates our understanding of free will and determinism as the true source of causality becomes increasingly obscure. The simulation hypothesis thus adds new layers of complexity to the age-old philosophical debate on free will and determinism, challenging us to reconsider the nature of choice and causality in our potentially simulated existence.